we will have AVHD, the first session here today, and the first presentation will be by Sonia from University of Cambridge. And, yeah, Hadi, is there any updates from the host before we get started, or we can just jump right into it? Or?
Just we will have group photo before lunch.
Okay, yeah.
And dinner we will happen at 7 p.m. in front of University. So you are all invited. So looking forward to meeting you there.
Okay.
But for lunch, I think we can still make for Mensa, right? So it was okay.
Yeah, I think it was perfectly all right.
So for lunch we will go Mensa, and for dinner University in front of you.
Thank you. Thank you. Okay, please.
Should I look on
If you just turn on your own camera, if you connect to Zoom.
Okay, I'll publish option because I cannot find Zoom again. This so that I can do the
That's true.
So, hello everyone. My name is Lina. I'm a PhD student at the University of Cambridge. And today I'm going to present the work that we did with Netflix, the effect of viewing distance and display luminance on the visibility of HDR video streaming distortions. So yeah, as everyone already know, video quality metrics are employed to optimize video streaming. This metric are basically used to optimize the video coding parameter to provide the highest possible quality within the client bandwidth limit. However, one of the biggest issues in this quality metric is that they don't really account for the display and viewing condition of this observer, and they are designed to predict the same quality score for the same test video regardless of the viewer environment in it. Despite actually the fact that this kind of factor like the display size, the viewing distance, the display peak luminance substantially affect the visibility of distortion. So to better actually visualize this, here we try to visualize the noise in an HDR image at two different viewing distances, 60 pixels per visual degree and 120 pixels per visual degree. We also visualize the visibility of noise at two peak luminance, 10,000 nits and 100 nits. So as you can easily see here, basically the visibility of the noise is decreasing when we are increasing the viewing distance, and it's also decreasing when we are decreasing the display peak luminance. And that is due to the fact that the human viewer system is simply less sensitive to lower luminance levels, and it's also in the same way less sensitive to higher spatial frequency in cycle per visual degree, so it is less sensitive to higher pixel per visual degree. So you can imagine that we can simply no longer assess the visibility of distortion in a video without really taking into account the display and viewing condition of this video. So because of this, we decided to create a new dataset. It's a publicly available dataset called HDR-VDC. That stands for HDR Video Streaming Quality Dataset across viewing and display conditions. So this is the QR code for the project website. So in comparison basically to previous datasets, and as far as we know, this is the first dataset that accounts for both the effect of viewing distance and display peak luminance. On streaming distortion, we are only considering compression and upscaling distortion, and for HDR videos. And we hope that this kind of dataset will be valuable for the community to train or test future metrics. So basically, this is an outline of this presentation. We're going to start by talking about how we collected the dataset. Then we're going to delve into analyzing the experimental results, and then finish by evaluating the existing quality metrics on the set. So let's start by talking about the subjective experiment. So we have selected 16 10-bit HDR10 videos with frame rate that range between 24 to 60 frames per second. We have 12 4K sequences and 1080p source sequences. We use other 1080p pieces, they had higher dynamic range. And we also selected kind of similar number of natural kind of scene, and then also generated scene, either animation kind of scene or gaming scenes. Also, because we are interested, like especially in the effect of display and viewing condition, we decided to select kind of like a concise encoding space or like distortion space. So we select two streaming distortion, which is the AV1 compression and the Lanczos 3 upscaling. So for the compression, we selected three compression level we use three CRF values for three compression level. And this CRF values has been personalized for each source sequence to basically ensure they have like kind of similar quality separation. For the upscaling, we selected two other resolutions besides 4K, which is 1080p and 720p. But for source sequences that were originally 1080p, we just downscaled them to 720p. And this downscaling has been done with Lanczos, and then all the test video have been again upscaled to the display 4K resolution during the experiment with also Lanczos. So in total, we had 9 distortion levels for the 4K sources and 6 distortion levels for the 1080p sources, resulted from the 16 reference videos to 132 test videos. But more interestingly is that we didn't only consider this distortion phase, but only another axis, which is display and viewing condition. So we selected a combination of two viewing distances and display luminance level. So because we basically have a 4K display, we selected first an optimal kind of viewing distance, which was 1.6 the display height, equivalent to 16 pixels per visual degree. And then we selected another viewing distance that was like farther away, which was 3.2 display height, equivalent to 120 pixels per visual degree. For the display luminance level, we selected basically two levels, a bright display and then a dim display. So the bright display has been characterized with a peak luminance of 700 candela per square meter and a mean luminance of 51 candela per square meter. And this was simply the luminance of our display that we used in the experiment, which was LG OLED G2 display. And basically, it's an optimal configuration. For the dim display, we actually simulated that by dividing the inputs like frames in linear RGB-BT 2020 over 8. And that simply gave us a display that is characterized with a peak luminance of 600 candela per square meter and a mean luminance of 5.6 candela per square meter, which we actually just measured from the display directly. So for the experimental procedure, so we decided to use a simple pairwise comparison protocol with active sampling. So there were like two main reasons why we selected the pairwise comparison. First, it actually offered more accuracy in measuring subtle differences, which is quite necessary here because we are measuring the effects of kind of like external factor like viewing distance and display peak luminance level, and we didn't know how much impact they will have. So we wanted to measure it as accurately as possible. And the second reason is that it offered us the opportunity to not measure the like overall preference of the user, but specifically the visibility of distortion in this kind of specific display and viewing condition. So because it's a pairwise comparison, we had basically two videos. Because both videos were 4K, we have used two 4K displays. And in each display, we can see like one test video and another test video here. And then the observer could basically switch between this test video and the reference. And then we ask them to select the video that is more similar to the reference. And by simply asking this kind of question, we were trying to just measure the visibility of distortion. So to better see it, this is an example of it. It's not running correctly here, but we have like our observer, like our two displays, and we have two different test video. And then the observer can switch and see the reference, and then switch back to see the test videos. And then they're going to select the one test video that is more similar or like closer to the reference. That means it has less visibility of distortions. And because we are using a pairwise comparison, we were actually able to also do a cross viewing distance comparison. So we have like different kind of viewing settings when we ask the observer to compare videos at the same viewing distance, either in a near viewing setting or like a far viewing setting. But we also had something more interesting that asked the observer at the same time to compare video that is closer and one video that is further away. And again, to make sure that nothing is going wrong in the experiment, we made sure to explain to the observer like the video, like you're going to see the test video here and compare it to the reference shown in this display. And then see another test video here and compare it to the reference on this display and select the one that has less visibility of distortion. And by using this kind of method, we were actually able to better measure in more accurate way this effect of viewing distance on the visibility of distortion. We actually want to do the same thing for the display luminance level. However, when we ran the pilot experiment, we found that the observer has high bias toward the brighter scene, even though it was obviously more distorted, they just couldn't choose the one that was dimmer because it's just like uglier. And so because we wanted to simply measure the visibility of distortion, but not really the preference, we decided to like split each session into 2 blocks. And in each block, the observer is going to view this video at 1 luminance level at each time, and they're going to compare videos at the same kind of luminance level. So in total, we had basically 4 sessions, each session for a different viewing setting, and each session lasting 1 hour. We had 30 participants, and all participants had normal or corrected to normal vision. And we made sure that all participants underwent a training session, and they had a very good understanding of the experiment task. And at the end of the experiment, we have collected 25,762 Paris comparisons. So after actually understanding how we collected these data sets, it's more important now to understand how we scheduled quality score and to analyze this effect of viewing distance and display peak luminance. So as Rafal explained yesterday, we simply use the Paris comparison software, which is, you can find the QR code here or the link here, and we scale all our Paris comparison to GOD scores. So a simple difference of 1 GOD unit between 2 conditions means that one condition has been chosen as more similar or closer to the reference 75% of the time compared to the other condition. The reference video has a quality of 10 GOD regardless of the viewing distance and the display luminance level. And simply lower GOD scores refer to lower perceptual quality and basically higher visibility distortions. So to visualize the results, here we're going to show the GOD score, but they are average over all contents for different resolution and for different bit rates. And we're also going to visualize it for different luminance level. So the pink one simply refers to a bright display, and the blue one is referring to a dim display. And we're also showing that for different viewing distance. So as you can see here, the solid line is simply referring to a near viewing distance, and the dashed line is referring to a far viewing distance. And here we're showing the confidence interval too. So the first observation that you can make from this is that you can see that the perceptual quality or the visibility of distortion is actually lower for lower luminance level if you compare between the blue and the pink, or for higher viewing distance if you compare between the dashed line and the solid line. And actually the quality is just the highest, or the visibility of distortion is just the lowest from the display that is viewed from a far viewing distance. Not only that, we actually found that the effect of both the display luminance level and the viewing distance is actually statistically significant. You can actually kind of see it with the error bar, but we actually measured that using the two-way ANOVA. And we found that the effect of the luminance level is actually small, and the effect of the viewing distance, again, compare the solid line with the dashed line, is a medium effect. And something more interesting is that if you look at lower resolutions, or lower bitrate and lower resolution, you can see that the difference between the same text condition that is viewed at near bright display and then at a far deep display has a difference of 2 GLBs. We simply mean that 90% of the people are actually preferring or finding that this condition is just simply has less distortion compared to this video, even though it's the same text video but just viewed at different kind of viewing conditions. So this kind of observation just shows us how much of an impact does this viewing distance and display peak luminance have on the visibility of streaming distortions. So after basically analyzing these results, here we're going to try to evaluate the existing quality metric on the HDR BBC dataset. So basically existing quality metric basically do not have the same characteristic. Some videos are basically made for videos. They can predict natively the temporal distortion in videos. Some metric are photometric, which means they can estimate the quality directly from the light emitted from a display. And some metric can actually account for the viewing distance. And basically we don't have all metrics that I can predict on all 3 axes. So to be able to actually evaluate all existing metrics, we needed to find a way to be able to account for this metric or to adapt them for this kind of display and viewing conditions. So first thing first, we needed to be able to adapt them for the display luminance level. So we did that by using a display model. And the reason why we use a display model is that basically each HDR display has its own kind of display from mapping functions. And so the color gamut of the radiometric output from the displays is just very different if you compare it, for example, to the color gamut of the REG 2020 that we're given it as an input in linear RGB. So our objective was basically to try to find this function or this kind of like model that can estimate the radiometric output from the display directly from the input linear RGB. And we did that by simply having like a lookup table with all the measurements from the display. And then by simply having that, we can also estimate the effect of the luminance level, because if you remember, we actually simulated the dim display by dividing this linear RGB by 8. So by simply doing that, we can also estimate like exactly how this video are shown on the display at each luminance level. And then second step is that we needed to also account then for the viewing distance. So you use that by using a rescaling function. So if you can't think about it, you can actually imitate this effect of viewing distance by simply like rescaling basically the image. So if you think something is more far away, that means you're going to see less high frequency in it. And this can be simulated by the filtering function in the rescaling. And yeah, so you can easily imitate kind of like effect of viewing distance using a rescaling function. And not only that, actually the rescaling function kind of have the same effect as a CSF of higher frequency. So you use that formula that was called SAS rescaling. And yeah, we found that the factor, like for the rescaling factor for near viewing distance was 1, and for far viewing distance was 0.5, which means if you are near viewing distance, you don't have to rescale your image or your video. Or if you are a far viewing distance, you just need to hide it. And then after accounting for the viewing distance, we also need to account for the non-uniformity of the absolute luminance values. Because if you think about it, we're still dealing with like the emitted light from the display, and most of the metrics are not photometric. So we need this kind of function that can go for the absolute luminance values to like perceptually uniform values in which the human visual system is sensitive to the difference between its values. So you use basically this Q21 encoding, which is just a known like encoding method that has a good model of luminance masking, banding, and glare. And that's why we use it. So after finishing all this pre-processing of the videos to be able to adapt the metric for the display and viewing condition, and also the HDR part, we then just inputted them to the quality metric. If it's a video quality metric, we just directly get the quality score. And it's an image quality metric, which is going to do an average over all frames. So here we're going to show the results. So we're going to use a Spearman correlation, and we selected just some few of the metrics that we evaluated. And here we're also showing the distribution of the correlation score. And we kind of generated this distribution by accounting for the noise in the data set. And that just gave us like a more of a fair comparison. And we also calculated the statistical difference between the distribution of correlation score between the different metrics. And here, if you see one line connecting between different metrics, it simply means that this metric has no statistical difference in between their prediction or like their performance on this data set. So that's what actually very interesting is that the fact that the best performance metric was HARPC, TOPIC, and IWSSEM, which are all image quality metric, SDR quality metric, and they don't really natively account for the display and viewing condition. And they actually do better than color video VDP and full video VDP that are actually designed for the specific task. And you can think about it that the reason why is simply because these metrics are just capable of capturing the streaming distortion better than color video VDP, which has been designed on multiple, like more broader range of distortion. And because of that, they are better at doing this task. And because we were also able to adapt them correctly for this effect of viewing distance and display peak luminance, they were actually to perform even better than other metrics. And that just shows that by simply employing this kind of simple method, we can like adapt any kind of existing metric that is good for this kind of specific task for the effect of viewing distance and display peak luminance. And we can now actually use them to better optimize the video streaming, which is pretty interesting. But again, this is just an observation that we saw for this kind of specific distortion. It may be different for other kind of distortion. So in conclusion, here we introduce a new data set called HDR-PDC that try to predict or measure the effect of viewing distance and display peak luminance on the visibility of streaming distortion in HDR videos. We found that the effect of both the viewing distance and the display peak luminance is statistically significant. And metric can be easily actually adapted to predict this effect by using simple display model starts with scanning and PS1 in one encoding. So that is everything for me. Thank you very much. And here you can find actually the link to the project page, which has all the data sets and the GitHub repository for like scanning the scores and everything. And this is just some nice picture doing the experiment at nearly viewing distance, far viewing distance, and actually like a far near viewing distance that you can actually see how it happened during the experiments. So thank you very much.
Question? Yeah.
Thank you very much. I think very, very valid and interesting work for our community and also for the field people. When thinking about viewing distance and luminance, the first thing that comes to my mind is display time. I mean, I know it would add like yet another variable,
Yes.
which makes things much more complicated again. But do you think that might have an impact?
So
Because at least for my viewing habits, display distance is of course different, but also when watching, for example, on a tablet, luminance is going probably down much more, specifically at night. But on the TV, maybe not so much. So what is your view on that?
well, again, the reason it's different is probably for other factors, also like the resolution of this tablet. So you have to like consider also the kind of tone mapping that is used in the tablet. That is quite different to display. I would guess that the viewing distance is in general like very effective, has a high impact for any kind of display, even for SDR or HDR. Probably the display luminance level has more effect if you are talking about HDR content. Because when you are HDR, you're talking about really high luminance levels. So if you are changing those, it's probably going to have higher impact. But yeah, but in a way we kind of like model this also, but by also adding a layer when we also accounted for the display model. So that's why I think it's not only interesting to account only for this display and viewing condition, but where you also need to always account for what display you are predicting on. So by accounting for that, you have also better way to like really know how this like distortion appearing on the specific display. Because again, even if I use like another HDR display, you may have slightly different results by simply like because of the tone mapping that's happening on the display. So there's like multiple factors that you don't usually cannot account for.
Thank you.
Couple of questions. One, I'm curious about the choice to basically model display luminance rather than actually adjusting the luminance on the display to adjust the signal. That I'm just curious about that.
Yeah, it's just that we didn't find a way to automatically do it during the experiment. We wanted to just directly change it. So we kind of simulated that by just dividing the linear RGB. Again, usually it's that because it's an OLED, you expect that by changing the luminance is going to be more linear. But again, we did it kind of linearly, but again, we have tone mapping of display, so it's probably not as linear, but it's just kind of an estimation. But if you want to do it in a more practical situation, for like actual observer, you want to have a display model different for each kind of luminance level and actually try to model that in a more accurate way. We try to only model it here for our specific kind of experiment.
And then that's a related follow-up question. I'm curious, did you test like how much does the display model contribute to the overall metric performance? Like if you just simplify by taking that out, how much is the performance drop?
Yeah, so actually we did that for all metrics, and we found that there's obviously better performance using a display model, but it was not statistically significant, which was more interesting. But I think that's because we are not really considering kind of chromatic distortion that may be more affected by the kind of display. But again, because maybe it's HDR display and even the color gamut maybe it's different if you use HDR display or like any kind of other display, I'm not sure. But we found that it's not statistically significant for this kind of specific distortion.
Thank you very much. I have a few questions. One is that, did you see any difference in the SDR and HDR content? Have you analyzed it or you only had the
I
HDR
only had
content?
HDR content.
Okay. Do you have any opinion that we may perceive differently SDR and HDR, I mean, in different viewing distances?
So there is already like previous works that did account for SDR, like the effect of viewing distance on SDR. Yeah, there was like multiple work that actually didn't consider HDR content. And yeah, one of them were actually your work, and you can actually see there is an effect of the viewing distance regardless. And there is also one study that studied the effect of luminance level too. Yeah, but also for like SDR image, and you can actually see this effect. But I don't know, like, I don't know how much of the magnitude, and I didn't verify how much of the effect size between an HDR and the SDR display.
In slide 15, can you elaborate differences between near far and far near? So,
Yeah, we just wanted to make sure there is not some kind of bias, because this is the display here and this is the display there. So we just like switch it between them to make sure that all the observers are in all kind of settings. We could have done like only one, and then we randomly choose between this like observer, but then we just wanted to have like because in near far you have like more conditions to compare, so we wanted to have like double the amount of session compared to like near far. So it was just better to divide it and do it in different kind of settings.
and the one in slide 22. So do you know why this happens? This is for the low bit rates, it's using impact of upscaling or the compression artifacts that is more visible.
So I actually studied the statistical significance for each kind of distortion, and we found like basically the effect is going to be more or less similar even for low bitrate or low resolution. I cannot remember, but I remember one of the two, either the viewing distance or luminance level had been more affected by either compression or like specific resolution, but I don't remember exactly which of which.
Okay. And do you think that the users are trained, like the results are different at the beginning of the session and end of the session, you think, or?
Well, you can expect that the user will get more used to the videos because it's a pairwise comparison. It's kind of in a loop kind of case. So we give them time to be able to really find which one is better. So you can expect that at the beginning they're finding it harder, and it's taking like usually it's like very slow in the beginning of the session and then get faster and faster because now they have an idea about where the distortion more or less are. There is kind of like training there, but it's not something bad because we do want to see if this distortion are visible at different viewing distance. But not because they are doing well in one session of near, they will do directly well in another session. So you see at each session, they will start to have to adapt more to this kind of viewing setting.
The last question, have you studied the impact of content dependency on the viewings?
So I'm planning to do that to see if there is like difference. So I saw that like, well, at least when I was looking at the plot, I saw that some content you can see less effects on them, like especially like the one that has very high contrast. But I didn't study it. I cannot give you like correct answer now.
Thank you.
I think we have a question online, Alexander.
Thank you. Yeah, very interesting work. I have a question exactly to this slide. Just for clarification, maybe you mentioned that and I missed it. So the reference, there's no difference between the luminances, right? I mean, for the data point on the very right? I mean, for the 97 megabits per second, there you only had one luminance, right? Or was luminance scaled there too? They are actually blocking at this 0.10.
Yeah, so basically we decided, so the reference video has always a quality of 10 GOD regardless of the viewing distance or luminance level.
Okay.
Because we are measuring just basically the visibility of distortion compared to this reference. So when you see here a quality of 10 is compared to this reference that is already at 10.
Yeah, it's interesting because I am supposing that, or it would be very interesting to check I mean, I'm not so much for the viewing distance that also, but especially also for the luminance values, it would be really interesting to see what the real difference is, right? I mean, if you have the very brightest version and take that as the reference, so to speak, right? And then you take any kind of dimmer version of the reference as the not so reference version, so to speak, right? I'm not sure how you would accommodate that with your experiment. I need to think about it, but.
I understand the question. So our experiment didn't really do that because we're not really trying to see the preference of like try to find the level when the viewer is basically going to not see the difference between the luminance level. So
yes, I know, because you actually you didn't compare the luminance levels directly, right? That's what you showed on one page. I came a bit late, but yeah, I remember you. Yes, exactly. This would have required this approach, and then people would have always preferred the brighter version, right? I see the point. Yeah.
If you use this approach, we're going to ask the observer to compare the test video here compared to its reference here. So he's going to all the time compare one test video to the reference at the same luminance level. So we always want to compare just, if you think about what we're trying to study is this kind of context when we have like our observer is already looking at things in a dim display. So we are going to have everything dim now, and we're going to see the visibility of distortion in this kind of dim scenario. So we have always a reference, like the best kind of case is going to be always in GOD regardless of the luminance level. And we're going to try only at that specific condition to see how much the distortion are visible or not, if it makes sense.
No, I understood that. I was more wondering how could you accommodate this this in addition, right? But I understand it's not possible with exactly the approach you took. Thank you very much. And another question with regard to the model picture, because I mean I saw your presentation also at QMX, but I didn't remember that you showed that there. So it's very interesting.
Yeah, we added like
the
more
last slide basically, I think, or this.
Yeah, the metric evaluation part we added compared to COMEX.
Yeah,
So
can you show the picture again? So there.
Model?
No, the where you have this violin plot kind of thing.
This one?
The last
Oh, the
one.
violin. Okay, sorry. I didn't see that. This one.
Yeah, this one. Yeah, yeah. I just okay. Yeah, what very interesting. Okay, so is this already published somewhere? This particular part here. This is very interesting.
It's going to be submitted for TIP.
Okay. Yeah, super interesting. Thank you so much. Yeah, I didn't see whether VMAF was included, but now I see it, so it's really very complete. Thank you very much. Excellent.
Yes.
Yes, question.
No, there was only one hand, which was yours.
Well, two questions. So first, this one.
Yes.
Because yesterday we had a very nice presentation from Rafa regarding color video PDP.
Yes.
And I can see it's still behind the rest of the group. So
Yes.
why so? And I cannot buy the argument that yes, because color video PDP has not been designed for streaming. This is what you said. If I cannot buy this because color video PDP is some kind of agnostic. You should be able to tackle with any type of music. So any kind of function. So why so?
Okay, can I?
Yeah.
Can I?
You can take that.
Yeah. So if you throw out color video PDP, very different distortions, it's probably going to overtake most of the metrics. If you have low frequency distortions and so on. Streaming distortions, if you have deep learning trained metric that was very fine-tuned for streaming distortions, you can correlate better. Why? Because, for example, I don't model visual attention. People don't pay attention to something in the background, they pay attention to faces, and I don't account for that. So there are some things that are impossible to capture in low-level visual models, and that can help improve the correlations.
I have like scatter plots.
Yeah. This is only very complex metric.
What did you say?
I do the view SSIM, it's not that.
Yeah,
This is the one that has attention.
Attention.
Yeah.
So that price is correct. That's the last one. There is and again, there's a lot of noise. Even though if we have successfully canceled everything, there's a lot of noise. If you take another data set, there is that.
Yeah, that's probably.
I mean, I can show you the scatter plot. They are in a hidden slide if you want to compare between the two metrics.
Yeah, if you had that.
I mean, this one share. I will need to start copy share and then share the other one.
What is the next step for color video?
Attention aware of color video.
So, for example, this is the HARP-C and this is the color video VDP. So here I'm just trying to show it, try to see how it's doing well for each viewing distance. If you just specify bright display or deep display and then just see the effect of luminance level if you specify near viewing distance and far viewing distance. And the dot here basically is the same test video, but at a near and then a far viewing distance. Just so you have a visualization of how well is this metric doing at predicting each effect. So as you can see, basically HARP-C is doing well. It's able to have this kind of linear relationship So it's basically able to account for this effects of viewing distance by simply using a Slattery scaling, and more or less similar to the luminance level. So, and if you look at it, it's actually more linear than if you compare color video VDP. So that's why it has this higher correlation, but both of them more or less are predicting this effect in a similar way. We also had like another analysis when we were trying to see how well the metrics are doing only on the task of the display and viewing condition, and both of them, they had no statistical difference between them.
That's why maybe you should use other type of figure on merit and correlation coefficient for to dig into more detail into the observation that not and other type of figure on merit.
Yeah, we have more in the paper, but I couldn't put all of them here.
Oh, by the way, because after I put this on the table for the attention stuff, similar on the that most of the visual attention model does not consider the luminance and the viewing distance.
Yeah.
And we can add similar trick as what we did for the quality metrics for visual attention, and it works a bit the same.
Yeah.
So similarly, this is something we wish in the IC back in the years, because same problem for as for quality and for visual attention, when you are deep learning method and everything, we don't consider the viewing condition. So we're trying to we are tackling the perceptual behavior. One conceptual question for me. I'm really confused with the concept of NGOD for reference sequence.
Well, I can
Because
put it up.
GOD, semantically speaking,
Yes.
if I get perfectly what happens there, it has to deal with comparison with something. And if you said that now a reference has NGOD, then I'm totally left with the concept. Can you clarify?
Yeah, I think that was maybe our mistake to define it that way, because this is not the, GOD is a unit of distance, and it's like absolute quality. The problem is that in previous papers, we used negative, 0 was the best and then negative, and people were super confused. So we started, that's actually shocking that we found.
I mean, I can make it 0 easily. That's like changing like one part of the code. That's because it's kind of a relative kind of scale. So we can scale everything using the anchor as 10, but you can change the anchor value to any value.
Yeah.
So I can have the reference at any value that I want, and then everything will be scaled to it.
And 0 means something, right? If you talk about GOD, you have to.
Yeah, we should use not a measure of quality, but measure of distortion. We try to be, because when you are plotting quality, you want to have higher thoughts, so that's why we choose that direction. LPIPs go the other way, and that's sometimes confusing.
Okay.
Okay, I think we need to move on to the next presentation, so thank you so much.
Thank you.
Nice presentation. And let's see. So we should have the presentation. 112 Thomas, which I guess will be online.
Yes, it will be online, so Tomasz is already, I think we're sharing.
Okay, so, hello Thomas, welcome.
Good morning to everyone.
Please go ahead.
Thank you very much. Can you see the screen?
Yeah, we see your slides. It's not in presentation mode. Maybe you can go to the presentation mode.
Of course, it should work correctly.
Okay, now it's okay. Thank you.
Thank you very much. Once again, good morning to everyone. I represent AGH University of Krakow. I am a PhD student under the supervision of Professor Mikołaj Leszczuk. And my presentation will be about the structure, the order of the stimulus presentation and its impact on subjective assessments. I have focused on the aspect of presenting a content, presenting layout of videos, how the internal relationship between the sequences of a video impacts the overall subjective assessment. We have conducted an experiment, very simple experiment, that focused on the study of two-dimension video quality and its and the verification how the order and the structure of stimulus presentation impacts the overall subjective assessment. I have focused on two aspects of the structure and order. I mean the repeatability of the videos. I mean how the number of views of particular videos affects the assessment, and how the quality, objective technical quality of preceding video sequence impacts the assessment of current video. We made two hypotheses in this areas. First of them is that there is a relationship between the number of views of video sequence and its subjective rating. Another one hypothesis was that there is a relationship between the objective quality of the video immediately preceding a given video sequence and the subjective rating of this video. Experiment was conducted in correlation and in a consent to the ITU-TP 913 recommendation. What is important that we have divided the testers into two groups. We call them regular and repeat groups. In a regular group, every tester was shown with the only one time PVS, and the PVSs were constructed in a way that 34 source reference circuit videos were all of them were degraded into 5 levels of technical objective quality. Together 34 multiplies 5 means 170 PVS sequences, and every tester has seen only once particular PVS. In the repeat group, we have introduced 3 repetitions of every PVS to have comparable number of PVSs. We have limited the number of SRC sequences into 12, and all of them also on the 5 levels of quality degradation. So together we had 180 videos presented to the tester, and every PVS has been shown 3 times for every tester. We used the data set that is described here. What is important is the picture. In fact, the picture shows the division of particular source videos into 5 degraded and VMAF assessed, objectively assessed source videos. We have qualified every video to one of 5 quality groups. Quality group A was were the videos with the highest quality. Quality group E were the videos with the lowest objective quality expressed in VMAF measure. Very simple data collection interface. After presenting a video, the screen for the assessment was presented. After the assessment, the next PVS was displayed. Together we had 35 testers. Due to the logic that we have implemented for assigning the testers to regular or repeat group, the number of testers was not equal or nearly equal. In a regular group we had 20 people, and in a repeat group 12 people and 23 testers in the repeat group. It was, as I said, due to the logic of assigning ID numbers to even or odd classification, no matter for this experiment. We had received results. Histograms will not tell you anything, but they confirm such a basic logic that in the videos of the higher technical objective quality were assessed better. Of course, it's obvious, but we have proven the correctness or the logic of the assessments in this way. We have eliminated outliers. Together, three tester results sets had to be rejected due to the outliers verification procedure according to P913 recommendation. And looking at the results, when talking about the hypothesis 1, we have observed that with the statistical significance on the assumed level, alpha level, for the highest level of objective quality, I mean for quality group A, the dependence of the subjective assessment on the number of views was demonstrated in the way that the first view was significantly statistically significantly better than the third view. Such dependence was observed only for the highest objective quality group, where in fact the mostly approaching the real conditions of video presentation and video displaying for people who watch streaming, for example. The interpretation was that the high quality PVS ratings deteriorate with subsequent views that can indicate higher criticism of objectively high quality content when we can see it next and the next time. For the high quality videos, the first view was best, and it was statistically significantly proven. For hypothesis 2, that concerned the dependence of the assessment on the objective quality of predecessor, we have observed for every quality group for no matter if that's quality group A with highest quality or quality group E with the lowest quality. If the predecessor was of the better quality, the assessment of given video was also better, and this statistical significance was observed for the highest level of video quality. Also for group D, but even without the statistical significance confirmation, for all quality groups, the phenomenon of better assessment if the predecessor was of higher quality was observed. For this reason, due to the results of this experiment, we have predicted several research areas for further exploration. First of all, I would like to focus on the correlation of the results we have achieved with other cognitive sciences. The similarity of subjective assessment to subjective assessments of different areas in psychology, in economics, for example, the shopping decisions, for example, in medicine, when we talk about the subjective assessment of anything, I would like to focus further on exploring the correlations of how the multimedia subjective assessment is similar or not similar to other sciences. Another aspect is the aspect of the bias that was observed, the bias related to the results of the experiment. If we can see the same video next time, we assess it worse than we can see it for the first time. Is it true, or perhaps it's not true? It's randomly affected. This is the area that I would like to move forward. Of course, another area can be the correlation of the obtained results, obtained conclusions with other factors. For example, how the human well-being or psychophysical condition can impact the assessment, and perhaps the other factors are more important than the order of presentation of the stimulus presentation. Two papers were published around this experiment, and I hope that the results of this experiment and the referred research areas that I have listed a second ago will bring us to the next papers, next articles. Thank you for your attention. I look forward to potential questions. Thank you very much for having a opportunity to present it today.
Actually, Charles had to leave for some meeting and he asked me to lead this session, to keep the track of the session in the end. So are there any questions? Okay, seems like there are no questions, so thank you, Tomasz, for your presentation. And we can
Thank you very much.
here. So we can move to the next one. And I understand the next one is Dominic Keller from Technische Universität Ilmenau. Dominic, are you there?
Yes, I'm here. Can you hear me and can you see my screen?
Let's go ahead.
Cool. Good morning and good afternoon to everyone. My name is Dominic. I'm from TU Ilmenau in Germany, and I would like to present today our open 8K HDR source dataset with the name ABT VQDB UHD2 HDR. Right, just to have some motivation. There's 8K HDR content that is increasingly available for consumers on consumer sites. Video quality models usually automatically measure and ensure video quality. However, they need training data. Yet there are no extensively validated models for 8K and HDR. And that is maybe, or what is maybe a reason, is that open content for research is very limited. We want to change that, and we want, or to be able to talk about that, I want to give you a small introduction about UHD. The UHD standards were created to improve the perceived quality and immersion of video. There are two standards, UHD1, 4K, and UHD2, 8K, and that is purely resolution change, so to enhance the video clarity. Additionally, these standards also include HDR, which is high dynamic range, that is meant to increase brightness, increase contrast for more natural images. On the right-hand side, you can see that in the SDR times, the open world was like downsized to SDR. Now we have a little bit more of contrast, a little bit more of dynamic range due to HDR. There's white color gamut that enables more realistic and vivid colors. Additionally, there's also HFR, high frame rate, to enable smoother shots, but this talk is not about HFR. Again, video quality models actually usually mimic human quality ratings so that you have an idea of what the quality of a video is based on viewers' interests, but usually they require reliable training data and many subjective ratings of different sources. And these quality models are also usually limited by codecs, color gamut, and resolution. And that's why usually if there's addition or an update to one of these factors that I showed, you also basically need to revalidate the video quality model. State of the art when it comes to these data sets is there's a lot of data sets when it comes to SDR and lower resolutions. Also, there's something for SDR and UHD1 and a limited number of SDR 8K data sets that are openly available. However, there's an even sparser number of HDR 8K stimuli or sources that are publicly available. However, what I need to say is there is some HDR 8K content available if you feel like buying it. This is what we took and actually had a student's project that was meant to create a data set. We followed the guidelines that were provided by a paper by Pinson et al. And wanted to have some diversity when it came to subjects. So we tried to have some actors with different skin tones, genders, ages, but also we wanted to have some diversity when it comes to what is actually within the content. So different landscapes, different objects, indoor, outdoor scenes, and so on. We also had some variation in lighting. So we had soft light and directional lighting, as well as artificial and natural light for variety of contents. We had different camera settings. We changed aperture and focal length, and we also varied ISO settings for noise and contrast. 3 different shooting methods we actually introduced. One was a classic tripod, then we had a gimbal, and we used a handheld with a neck strap to shoot the videos. Different apertures, different shutter, or actually one shutter speed, 1/125 seconds, and we used ND filters to adjust to light. For the post-production, we used DaVinci Resolve and even had some selective noise reduction, which I will talk about in a second. To give you an idea what the dataset looks like, on the right-hand side, you can see actually the 31 sources. So different sources with different or unique IDs and names. We have some indoor scenes like the ones that are highlighted right now, which are hobbies, conversations, dancing, knitting, interview. So just some scenes that you might expect in a movie or in an internet video. We also had some outdoor scenes, again, some sports, some hobby activity, and just some landscapes that you usually have there when it comes to shooting outdoor videos. The dataset is available under the link. In the end, there will also be a QR code if you want to have a look from your phones. Right. Just some numbers for creating the dataset or how the dataset was actually recorded. We used a Nikon Z9 camera with a 24-70mm lens. We recorded in the highest resolution of the camera, which was above 8K actually, to close to 60 frames per second in the NRAW format, and then actually did some cropping to get the source resolution of 8K 7680 by 4320 at 59.94 frames per second in the FFV1 codec. Almost all stimuli, almost all sources are 15 seconds. Only the IDs 21 and 28, highlighted on the right, Powerful Sky and Swan, are only 11 seconds for 2 reasons. The Powerful Sky was slightly increased in speed, so there's a little bit more change, a little bit more difference in the video, and that's why we didn't have enough material. That's why it's only 11 seconds. And the Swan decided to move too quickly in the end, and that's why we also cut it away, because there were some issues with the lighting in the end. We have 16-bit full range bit depth in the color format RGBA 444. Color gamut is BT2020, transfer function PQ, and the matrix coefficients of BT2020 non-constant. Right. We did some preliminary analysis to have an idea how good / how the data set actually is. And we looked into sharpness and coding complexity for the beginning. Therefore checked for SI and TI, what you can see on the bottom right. X-axis SI, TI is on the Y-axis. And you can see that the averages of SI range between 0 and 50, depending on the scene, and the TI ranges between 0 and 25. To have an idea of the actual benefits, we rescaled it to 4K and then upscaled it again to 8K to compare. And we checked for PSNR SSIM. On the top right, you see the SSIM score, and you see a high Pearson correlation of, or you don't see that, but you gotta believe that a high Pearson correlation between the two numbers of 0.93. There are several videos that are above 0.9, 19 sequences, some sequences between 0.8 and 0.9, and 3 sequences below 0.8, which shows that there is some similarity between the 4K and the 8K contents. However, there seems to be an addition, there seems to be more within the 8K contents that is not in the 4K contents. We also calculated the criticality score, however, could not reach all the measures that were proposed, I think, in the Pinson paper. Still, we had some variety there, so that there is a, let's say, resemblance of real world, and there's also a complexity that makes use of the 8K resolution. Right. However, what we need to say is, and that's something I'll think I want to talk about, is we had some issues with noise, especially in the dark scenes, and noise has an influence on the TI value and therefore also on the criticality value. So there is some noise. We did some noise cancelling when it was useful and when there were basically no real 8K benefits expected from parts. But still, due to low light performance of the camera, there was some noise there that also could have an influence on TI. We did some preliminary analysis for dynamic range too, and used the dynamic range measure DR from that source, converted it to only Y, scaled to 0 to 1, and mapped then the signal to 0.01 to 1000 candela per square meter, excluded the max and min values, and then measured the dynamic range, which would be the max in that range of 5. We have 2 IDs who use the actual full range, and quite a lot of them who are close to that. Some of them, like 17 and 18, have limited dynamic range due to Steam, that is the cooking videos. But in general, I also would say that we have quite a variety of different dynamic ranges, which is also something that resembles nature and actually scenes that you would see in videos and movies. I want to give you a small glimpse into the dataset. Please have in mind that this is an SDR render, an automatic SDR render of the different scenes, but so you have an idea how they actually look like. Right. To conclude this talk, we actually created the 8K HDR video dataset AVT video quality database UHD2 HDR, which is above 3.3 terabytes. So if you want to download it, please have that in mind. It is made publicly available for scientific usage under that link, QR code in the next slide. It's, we think, a good base for subjective testing and the subsequent training and evaluation of video coding algorithms, quality models, and metrics. We did a preliminary objective analysis that indicate benefits of the dataset, but subjective tests and a more in-depth objective analysis is still needed. So we hope that this is a contribution to the open research and the 8K HDR video quality. With that being said, thank you very much for your interest. Please feel free to contact me under that email address or have a look at that QR code to get the database. Thank you very much.
Thank you. Are there any questions? Yes, please.
Hi, can you hear me?
Yes, I can hear you. Thank you.
Okay. Thank you for the presentation. This is a very nice contribution. What I would recommend is to measure MTF, modulation transfer function of the camera, just to see how much resolution the camera can actually resolve. And just if you publish paper, I would recommend including that information. And this can be easily done using a slanted edge technique and this open source software that can do it for you. So it's not difficult to do.
Thank you very much. Yeah, we had actually some look into that. We also looked into the lens. And there's actually also internet sources that point out that the lens actually is capable of having a point spread function that enables or that makes use of the 8K resolution. We also had a look into the camera, but we did not really put some proper measurements at that stage yet. So thank you for the input.
And was it, what was the frame rate of those videos?
59.94 frames per second.
Oh.
Any further questions?
Did you do any experiments with compressing those sequences, so to see kind of how easy or how difficult they would be to compress?
We actually did a subsequent analysis in that yet. So we did some subjective testing with that already. So yes, we did that, but since it's not published, I cannot really talk about it yet.
Okay. Okay.
Any other questions? No? Okay, if there are no questions, then thank you, Dominic.
Thank you very much.
Thank you, and let's move to the next presentation. It's going to be given by Syed Hudin from AGH University of Krakow.
Hello, sir. Yeah.
Please share the screen.
Please. Why? Can you? Hello.
Please go ahead.
Is it? Yeah. Hello, good morning. My name is Saeed. I'm going to present my experimental setup for experiment I conducted. The title of my work here, it is QE-based objective analysis of low latency algorithm, which I carried out in Dash.js environment framework. I will give an overview of the Dash network, how it carry out and how it tackle the video sequences. So you can see it here. It's the video stream. We are having the original video sequence, which is encoded using different representations with the low quality and higher qualities. And then those representations are kept at the main server, which called streaming server, video. This is another scenario. You can see I have two video sequences, which is encoded on two different bit rate. I put it, for example, here. One is encoded on 1 Mbit, and the second is encoded on 4 Mbit. Those two different representation, it is basically deployed to a streaming server. Then on the client side, based on their network capacity or bandwidth, they can request either opt for higher quality, either lower quality. So that's how it works. The issue here is basically when the video, we put it on streaming, there are a lot of mechanism which could possibly impact the video quality of experience. And those are basically the stall, which is art interruption, the quality switching pattern, which probably some algorithm it basically do the quality switching quite often, which possibly impact the video quality. And then we have the segmentation strategies. Either we opt for higher segment or lower segment, with segment with higher duration or lower duration. And those all combined can be optimized using adaptive bitrate algorithm, which could increase the perceived quality of the dish stream video. So that is hypothesized generally. I can classify the adaptive bitrate algorithm in two halves. One half is basically classical bitrate algorithm, and the second half is low latency adaptive bitrate algorithm. So those are two, and you can see it here. The classical ABR algorithm are basically classified in bandwidth base and buffer base, and the low latency is over here. It is quite recent phenomena, which is L2LL and LLF+. And I carried out evaluation considering those ABR algorithms, the two suite of ABR algorithms. Before I start experiment, streaming condition could differ. So we possibly have different network profiles, which really based on the network capacity, the bandwidth we use. In my experiment, I went for this 4 network profiles. So you can see I could opt a streaming with the very lower bitrate, and then I could switch to a higher bitrate. And then this later two, for first few segments, if I have 20 segments, for 10 segments, I pass through and stream the video with 1 Mbit, which is lower, and then I increase in the middle, and then we pass 4 Mbit rate, which is relatively higher. Then we check the quality. And the later is for first segmentation, we first opt for the higher bitrate, pass the higher bandwidth, and then I reduce the capacity to 1 Mbit, and then I see how that behave and how it could impact the quality of those video streams. So those are the network profile I use in my experiment. The source data set we created is established data set used by created by Klagenfurt, which is the host of PKG as well. And I opt the data set. The reason was it is basically specialized for dish stream, number one. And then I was looking for segment duration relatively a bit higher, not 2 seconds, 4 seconds. So that was quite desirable for my experiment. And I extracted 30 segments, and the video sequence was like 300 seconds long. In every dish experiment is like the video quality is based on the bandwidth it passes. So we possibly have encoding later, like we cannot keep or store a video stream in one quality level. So I have here a sample. You can see it here. I have video resolution, and I kept it with the data set has encoded it with different bitrate, which ideally it happened like this. And you can I can have video resolution encoded with various bitrate. I can differentiate it, like make a difference of 50 kbit, 100 kbit, 1000 kbit. It is another mechanism of creating an encoding ladder. I can have a difference of 1 Mbit, 2 Mbit in middle. So this is a sample where we have low resolution and high resolution encoded with various bitrate. The evaluation framework I use, it is DISH.js, which is the industry-wide specific evaluation framework used for evaluating streaming sessions, ABR algorithms, and various buffering events and all those. It is we call it reference client, and it is playback by MPEG-DISH, and it is JavaScript base, and we can do a lot of scripting to extract various values regarding our streaming session, like interruption, video bitrate, and I can deploy it in my metric. So basically we analyze after the streaming, completing the streaming session. I know the bitrate of all the downloaded segments. So that is one metric I have. And then we have the bitrate changes among okay, if I have 20 segments, so first segment is downloaded by one specific bitrate, the other segment might be different. So that is how the bitrate changes. I noted it down, which is related to our switching patterns as well. And then after one streaming session, I have an average bitrate change as well. Overall, I can see how much the bitrate is then change in one streaming session, like 300 seconds. And then I can calculate the average bitrate per session as well. Here is an example, a scenario in my work. Like, for example, I have 6 segments here. The first segment is carried out basically downloaded at 100 kbps. The second one is 100 kbps, and I can see it here how it varies between each segment, and it will give me the value of switching patterns among sessions. We can observe here 3 bitrate changes in that specific scenario, and I can calculate average bitrate metric. For example, I have 20 segments, and then I can calculate the average for what bitrate, like on an average base, it used to download that entire video sequence. So that, and the small bitrate change between segment 3 and 2, so we can observe like a frequent, bitrate change, or it is static, or it is if there is no bitrate change. So we can opt those strategy here, and I can analyze. And I can observe the large bitrate changes as well, or frequent bitrate changes, which is again related to my quality switching metric. Now I have all the data, like bitrate. I can have the bitrate of each segment. I have the number of bitrate switches, how quite often it switch to the other bitrate, and then I have the rebuffering events. If it rebuffer one time, it rebuffer 2 times, 3 times in a session. I have that value as well. And then I have the entire duration of each rebuffer. And it is like 2 seconds, 1 second, 3 seconds. So that is another metric. Nice. And here I can show the preliminary results. We can see the bitrate, like if the metric is based on bitrate. I have 5 algorithms here: dynamic, Ebola, throughput, L2LL, and LLO plus. And we can see it clearly here that if average bitrate changes, so how the different algorithm yield on a specific network profile. So we can see it here, the average bitrate, like the low latency algorithm. This is the preliminary result. So I can see it here that the L2LL, which is the low latency algorithm, it yield the highest bitrate. It means it have the highest quality, yield the highest quality, as compared to this traditional suite of algorithm. So this is one observation we can make, and then we can find the average. Or we in the next stage, I'm calculating like the cutting point or the average of each bitrate stream and which algorithm react or behave in that specific metric. Over here, I calculated like the number of switches. So you can see it here. The standard algorithm experience video rate switches quite often, which is not favorable, and that will possibly impact the QoE as well for the video and the user perception as well, persuasion. So the standard algorithm, it has the more frequent switching, and if there is more frequent switching, it will be there will be interruption. In the next, if I can see the average interruption. So here I can see the dynamic is averagely the traditional. They have the more interruption as well, or L2LL as compared to the low latency as well. The buffering time, the L2LL, it has the most power. It means the low latency algorithm. It achieved the highest bit rate, but it have the interruption as well. So it compromise over here at heart, which is again not good for who are yielding overall QV. So those are the base thing, the base metric which I'm calculating, and I will base those values on my metric. Like for example, as I said, I want to find the average value which each algorithm is performed reasonably fine and achieved a very good with low interruption or higher bit rate. This is one thing. So I will conclude my experiment here. The next stage in my experiment is to basically I have an objective evaluation. So I'm going to I deployed the video stream after the streaming session. So I'm going to throw it to user evaluation, which possibly correlate the subjective opinion with my objective evaluation. This is another. And secondly, I'm going the work I carried out. It is based on MPEG-DASH, where we use segments. And now I have another framework, which is CMAP. That is basically chunk-based. We use chunk-based streams in CMAP, and that is basically giving me I can calculate the latency using a metric by CMAP. So this is the ongoing work which I need to compare how my existing evaluation framework work under CMAP condition when I carried out and measuring the real latency. How is the measure? That thing, and I will conclude it over here in this existing work. I try to compare the traditional suite of ABR algorithm with low latency algorithm. And my model is based basically on a video quality, rebuffering events, and video quality fluctuation. And I'm trying to measure the quality of experience based on that model. So that's for us. And if you have any suggestion at this stage, it will be welcome. Thank you so much.
Thank you. Are there any questions? Okay, yes, please.
Thank you, Said, for the presentation. I'm just wondering what was the target latency that you set up for the experiments, specifically for the low latency ABRs. I think you can set up a different kind of target latencies.
Yes. Basically, this existed work, it is only measuring the low latency under the current technological implementation which I have, which is based on MPEG-DASH on a segment. So it is not giving me the 100% measure of what mean by low latency, number one. Okay. So I just compare, now try to the traditional algorithm using this low latency based on this video quality rate and rebuffering events, which I do it. So normally I put like TC, it is measure 1.5 something. I will show you here. That is Linux based TC. Hello.
Yes.
Yes. Sir. So as I mentioned that.
Fine. Thanks.
So yeah.
Okay.
Yeah.
Thank you.
Any other questions? Great. If there are not, so thank you, Said. And I think we have the last 15 minutes in this session to go to the last presentation. So it's also the presentation from AGH University of Krakow, and the presenter is Abhijit Gupta. They are there?
Yes, sir.
Okay, great. So go ahead.
Is it visible?
Yeah.
Yes, yes, we can see. We can
Okay.
see it.
Okay. First of all, I wish you to a very good morning to all BQEG members. I am Abhijit Datta, a third-year doctoral student of Information and Communication Technology from AGH University of Krakow, Poland, under the Dr. Mikołaj Leszczuk. Today, I am going to present my current research work. The topic is a crowdsourcing study of video quality assessment. As I mentioned in the last BQA presentation last year, future research could explore the use of more scenarios and the evaluation of the summaries by end users to assess their usability and effectiveness. The selection of approach for evaluating subjective quality is contingent upon different human influence factors. That means age, gender, educational qualification, etc., and warrants meticulous consideration to guarantee the accuracy and consistency of the outcomes. Now, this work includes the exploring the different segmentation and the selection methods and evaluating the proposed technique on larger data set. This study investigates the evaluation of subjective video quality utilizing short video clips on a crowdsourcing platform. Introduction: the rise of online video material in the digital era has increased the demand for efficient quality assessment methods. The use of crowdsourcing evaluation has emerged as a potential method as assessing user opinions on video quality. This strategy leverages the collective wisdom of online communities to acquire a wide range of feedback. Processed video sequence and user-generated content are important parts of the current multimedia environment. Both types of content present distinct difficulties when it comes to assessing their quality. Moving on to the main body of the presentation, the flowchart. This study aims to examine subjective video quality evaluation by using short video clips on a specialized crowdsourcing platform. Our objective is to clarify viewer impressions of video quality in various genres of content and quality levels by using absolute category levels and monitoring response times. By conducting a thorough experimentation and analysis, our aim is to enhance the existing knowledge on video quality assessment and its impact on multimedia technology and content developers. The results indicate that videos of fair quality regularly received higher timings, suggesting the presence of potential biases in subjective evaluations. The study emphasizes the significance of considering contextual variables, such as monitor resolutions and experimental design, when evaluating video quality. The findings improve our understanding of how users perceive video quality and provide valuable insights for future research on multimedia technology. We here used the single stimulus continuous quality evaluation. It is a method that requires viewers to continuously rate the quality of a video presentation as they watch it, providing a real-time assessment of the video quality. Scientific experiment. In this research, we present a crowdsourcing experiment for the determination of the quality of the video clips. The experiment aimed to evaluate the effectiveness of the crowdsourcing platform and to investigate the impact of the different influence factors in the quality of the videos. We use an online crowdsourcing platform, such as a website, to recruit participants for this experiment. The individuals were provided with a set of guidelines based on the ITUT P910 guidelines. Step-by-step guides provide detailed and sequential instructions for users to follow, enabling them to complete a task without requiring additional video or text explanation. Where the ITUT P910 subjective video quality assessment methods provides a standardized framework for conducting subjective video quality assessment and focusing on the evaluation of the video transmission services. Next slide. Ensuring an exceptional experience for viewers is of utmost importance since it directly influences user satisfaction and engagement. Quality of experience matrices offer significant insights into user preference and habits, helping content creators and platform developers refine their offers. Subjective experiments are crucial instruments in this effort, allowing researchers to record subjective impressions and the preferences of viewers through the controlled evaluations. Age is a key demographic factor in video quality assessment, as individuals of different ages may have distinct perceptions and preferences when evaluating the video content. And another aspect of the gender is a demographic characteristics that captures an individual's self-identified gender identity, which can have unique implications for video quality perceptions compared to the other demographic factors. The last one, the geographic location, refers to the physical place or region where the user participating in the video quality assessment is located, which can provide additional contextual information beyond just age and gender. Crowdsourcing is a technique that involves dividing a task into smaller parts, assigning them to multiple individuals for completions. The collective intelligence of a group can be harnessed to perform tasks that are excessively difficult or beyond the capabilities of machines operating independently. This involves assigning tasks to multiple individuals, typically using a digital platform. This approach involves disseminating a concise overview to a wide-ranging audience through an internet-based platform, subsequently gathering feedback from the individuals comprising that audience. Although this approach has the potential to produce a substantial amount of information quickly, the effectiveness of feedback may vary depending on its execution. Each person is responsible for independently doing the task, and the combined results are used to determine the result. Furthermore, the utilization of crowdsourcing can significantly reduce the time and financial resources needed for video quality assessment. Hence, enhancing its efficacy and accessibility, the use of crowdsourcing for the assessment of video quality has significant potential for future advantages. The experiment has conducted using a customized website that has created utilizing programming languages such as PHP, HTML5, and JavaScript in our AGH University web server. This website allowed for the assessment of the subjective video quality. A total of 47 engineering graduate students participated in providing ratings for 170 short videos using the absolute category rating scale. Participants utilized the platform by assessing it through LAN-connected laboratory computers. The experiment includes a selection of 170 short video clips taken from various databases such as Netflix, Cable Labs, Video Test Media, etc. All videos were of full HD resolution, specifically in the 1080 into 1920 pixels. The experimental procedure involved the random presentation of video clips to participants with durations ranging from 9 to 21 seconds. The experiment was only conducted on Google Chrome in incognito mode to eliminate extraneous interference. The experiment was completed in a total duration of approximately 55 minutes. After completion, the participant received a message confirming their successful participation. I did this experiment with another colleague from our research group. He gave me the videos. The video voting poll, the individuals were asked to vote about the quality of the video clips based on the ITUT P910 guidelines. After seeing each clip, the participant evaluated its quality using absolute category rating scale, which includes categories such as excellent, good, fair, poor, bad. Participant assessments were recorded in conjunction with response times, which were qualified and quantified in milliseconds. Participants were explicitly advised to refrain from engaging with the videos during playing, such as pausing or right-clicking. Following completion of each video clip, a voting page would be displayed for the evaluation purposes. The response time, which refers to the time taking to make high-quality judgments, provide vital information on the cognitive processing and the decision-making involved in subjective evaluation. The statistical analysis was conducted to compare decision times in various video quality categories. Response times were calculated and compared for each quality level. For an analysis of the data revealed trends in quality ratings across various degrees of video quality. Significantly, video clips of fair quality regularly garnered higher scores in comparison to the other categories, as participants dedicated more time to carefully consider the much more longer response times reported for videos of fair quality. That means 1,867.19 millisecond. The table displayed descriptive statistics such as average values and variability represented by standard deviations for reaction times in various quality categories. Although all short videos are in full HD clips and fair quality resulted in lengthier response times exceeding other categories within a 5,000 millisecond limit, that means 5 seconds. The influence factor of the study included a total 47 participants, including 5 women and 42 men. The sample consisted of individuals of various moods, and tiredness, ensuring the representative sample of the experiment. The influence of the monitor resolution, the display in the resolution between the video clips 1080 into 1920 and the laboratory monitors 1440 into 900 may have impacted participants' quality evaluations and their response times. Future research should investigate the impact of monitor resolution on subjective quality assessment and take steps to control for this variable to ensure the accuracy and the consistency experimental findings. The device types refers to the type of the device used by participant to view the video content, such as desktop computer or mobile phone or tablet. This factor can impact the perceived video quality compared to the other viewing condition. The device bias refers to the influence that the type of device used by a viewer can on their perceptions and the assessment of the video quality, as different devices may have varying different display capabilities and resolutions. In summary, this research improves our understanding of subjective video quality assessment and establishes a basis of future investigations in this domain. To enhance the video experiences for global audiences, researchers and practitioners would focus on understanding and catering to user perceptions and preferences. These are the main references which I used for this experiment. Till now, I published one paper, and the one accepted the last week, and one is submitted in this crowdsourcing experiment. And thank you very much for your kind attention. I will be very happy to hear any questions or comments from you. That's all.
Thank you. I believe we still have some time for questions. Are there any questions? Okay, so I don't see any questions. Thank you. And this actually concludes our ABHD session. I understand that, well, we're like perfectly on time. So I believe it's time to close it, and the next will be IMG. I understand that IMG chairs are here, so there will be someone chairing the IMG session. So yeah, let's have a break, 15 minutes up, until 11 Central European summertime. Okay, thank you.
Hello, everybody. Welcome to the IMG session. We will have don't know the number, but like 5, 6 presentations. 3 of them are not related to the this common activity that we are doing, but the rest are all related to that. So we will start with 2 presentations from Kamran Javidi and Maria Martini. Kamran, are you there online?
Hello, good morning. Yes, I'm ready. I'm online. Hello?
Hello.
Yes, I'm ready. Yeah, I'm online.
Okay, so maybe you can share your slides.
Okay. So shall I start?
Yeah, now it's good. Yeah.
Okay.
Thank you.
Hello, everyone. Good morning. I'm Kamran Javidi from Kingston University. I have 2 presentations today, actually 2 different data sets in one presentation. It's a light field data set. The first one is the images, are images in that data set, and the second one are some videos in a data set. A display FOV specific light field image dataset KULF-TT53 is the name of the dataset and the first presentation, the first part of the presentation, with content characterization and objective quality assessment. The motivation for creating the datasets are visualizing and carrying out some subjective tests later on, and using the specific light field display for this purpose and for this reason. The light field display that we use has a FOV of 53 degrees and is only a horizontal parallax display. And like I showed in this image, we have a specific valid viewing area, VVA, that so it allows all the viewers to allocate and position in this area. The only constraint is the geometric constraints for the viewers and the space, and depending on the distance from the display. The available data sets until now, most of them are not mentioning this FOV. The main challenge of our data set, mainly the first one, was to specifically design our data set and capture the contents for the specific circumference of them, the angle of them, 53 degree, to be aligned with the FOV of the display. So because it's a very important challenge, for a very, very important challenge for us. So the first data set has 7 different contents, all images, and are particularly captured for 53 degrees around the models. The name of models are depicted below each sample. And there are 2 different versions in this data set. One version has 140 views and the other one has 70 views, because it affects directly to the angular resolution of the content visualization later on. And we captured all, and we utilized turntable where rotating or turning clockwise. Also, the compressed version of the contents are available. This is the link that the dataset is available over there. I have 2 videos captured from the display to show how it looks like, but the quality is not that perfect. But you see by moving along the display, live display, you can see different dimensions, actually different perspective of the content, depends on your position. And obviously it's a horizontally, it's a horizontal parallax, and then if you move from one side to another side horizontally, you can see different dimensions and views. The other content is a dot content that you can see the same thing. If you move in front of the display, you can see different parts of the object. So one of the benefits of the light field displays is that without any goggles or any glasses, you can, with unarmed or naked eyes, you can watch the contents. So it's one of the use cases which is very important. So the effects of angular resolution that I mentioned, 140 views and 70 views previously, so it shows itself here. If we zoom on a dark part, the body part, you can see if we have a lower number of views, actually lower angular resolution views per degree, slightly the content, the text on the body is blurry and is not readable in compared with the higher angle resolution. So in two different images, the left one is the lower and the second one is slightly. Because it's zoomed, maybe the quality is not that perfect, but slightly still, it shows that there is some differences between two different angular resolution and between them. After we created the contents, so we carried out the content characterization on them. We used different features, 3 different features, spatial information, but on a views, not on a frame. On available views inside a frame, 140 views
La
actually.
cosa es que ahora hay vida.
Pardon?
No,
SI view pulled over views and temporal information, again, over the views and the colorfulness are calculated and depicted in the figures. So SI and TI, when we calculated SI and TI, the maximum value of the overall SI overview and TI overview is selected as a final SI and TI. But for colorfulness, the mean value is calculated as the final value of the CF. So just to note that TI is over the views and it's not over frames because we have multiple views in our frames, and TI temporal information overview is calculated over views. Yeah. The next step was quality assessment of the contents. 4 different encoders are applied, video encoders are applied on the contents and created a video, and then the PSNR and SSIM is calculated. So the different compression ratio are achieved, and the video is created from the views, and then above video encoders are applied on them, and then the PSNR and SSIM are calculated based on the decoded version of the contents and the original version of the contents. And the compression ratio is calculated based on original size over the compression size. In the figures, it shows that AV1 shows a better performance in compared with the other encoders. Clearly, it's evident in the figures. And this is the address of our website, the paper that we published for this data set. The next data set is a video data set, particularly designed for light field. Actually, it's light field, and we use a Planoptic video camera. And the name of the data set is KOL-FR8. Again, we have content characteristics and quality assessment are involved in the data set. And the others are Kamran Javidi, me, and Professor Miriam Martini. So a little bit about the Planoptic camera features. Raytrix R8 is utilized for this test. Is specifically designed for Planoptic capturing. The maximum resolution is 2 megapixel. The maximum frame rate is not too high, is 30 frames per second. Focal lengths are this range, and we pick 35. And F number, the range, and 2.8 is picked. The field of view, width, height, and depth are respectively 2014 9 millimeters. Minimum and maximum working space distances are 170 and 350 millimeters, and depth resolution is 0.09 millimeters. So it has different versions. This product, Raytrix company, has different versions of the Planoptic cameras, and particularly R8 version and model is used for this test. So in this lightweight data set, which is video, like I mentioned, we have 6 different models and 6 different videos. Actually, out of these 60 videos, we derived 366 disordered light field videos. A massive number of videos are derived. Each video frame includes 25 views inside that itself, and 10-second videos are created out of each content. In total, 300 frames for each light field video, and the data set is available on our website. publicly available. The models, the utilized models are depicted here in the slide, and the geometry and the sizes of them by order. And only for the last part, we have two models we used in one video. The previous one in the water video, we used two models of fish and the turtle, but the geometry and the sizes are depicted here. The first step to capture the contents was the the camera calibration. We used the application, the Raytrix application, to calibrate the camera and use the platforms and the frames for this calibration. The next step was capturing the contents, actually videos, recording the videos. The camera is in its fixed position, while the object as a wind-up toy was in motion. So, and then we extracted a frame, a 5x5 quilted frame out of the API, Raytrix API. Then for 10-second video and 30 frames per second, 300 frames are created and are restored in a sequence of frames to create a video. And then by using a buffer of API, we extract the views out of each frame, and for further analysis. So 20 views are extracted out of each frame. And next, when we created the contents, is the content characterization. So for content characterization, specifically for this data set, we use the central view of our frame, actually as a quilted frame. We extracted the central view for analysis. So different color spaces are applied onto this central view for, again, content characterization. For spatial information, again, on a view, and TI again on a view, and colorfulness. Moreover, motion vectors are calculated and are created in the figures. So, for example, these two images and figures are based on the Y component only for the SI and TI overview, and the colorfulness versus the temporal information and the spatial information. And obviously for the spatial information, magician content shows a better performance in compared with the other one. And the temporal information, the B content has more temporal information. The next slide is the figures that we used, V component on the HSV color space for motion displacement versus spatial information and temporal information. And the why we use the HSV, because when we extracted the V component of HSV color space, it showed a better performance in case of motion displacement, because the B content has high motion inside itself, and we noticed that V component and using the motion displacement vector displacement analysis can calculate and find the better motion vectors in compared with the other color spaces. So we extracted different components of different color spaces are depicted here. The L component of HSL, it comes from left to right for each model. L component of HSL, V component of HSV, L component of LAB, and Y component of YUV for different models are created. And this image is actually I mapped the motion vectors, the total motion vectors on the one sample view, and it shows in the B model, which is related to the V component of the HSV. It shows more motion vector detected around the wings, the B wing, because it's moving very fast, and it creates a motion blur, blurriness for the content. So because of that, we use the V component. Later on, we calculated the quality assessments, PSNR and SSIM quality assessment. For this specific data set, we used AVC, HEVC, VP9, AV1, and VVC for for 4 different preset speeds. We calculated, and based on obviously we use the frame, the high actually resolution frames 9600 in 5400 pixels in the quilted frame. We use these frames, high resolution frames, for applying the encoders and then evaluate them for different quality metrics. So based on our evaluation, AV1 shows a better performance in compared with the others in both cases, and AVC shows the worst performance among all encoders. And for SSIM is the same. And we will apply and we will test our contents, our data sets, both data sets for the subjective test later on. And we have a purpose to compare the results out of the subjective tests with the objective evaluation results in future. And the data set is published in this paper, a reference is added. So in the diagrams, we had a big range of, actually large range of the bitrate ranges, 1 to 30 megabit per second are applied onto these contents, video contents. Thank you. It was my presentation. Thank you. If you have any questions, please. Yeah.
Thank you, Kamran.
No
questions? There are some questions.
Do you know what was the baseline between neighboring views in your camera? Like how many millimeter baseline do you have?
Well, for first data set, you mean, yes?
Yeah, for the one captured with Raytrix camera.
So Raytrix camera, you mean the baseline between the lenslets?
Between the views, because now obviously you transform your planoptic representation into view representation, and you essentially simulate kind of like displacement of the camera in vertical and horizontal axis. So if you were to simulate those small cameras, what would be the displacement, the displacement of those cameras?
Displacement for which part? I can't get your question. For content characterization, you mean for motion vectors?
No. If you go back to those images,
this one?
No. If you have like this 5x5 matrix of images.
Oh, wait. Yeah, this one. Yeah.
It's like images captured from different positions.
No, the planoptic camera design has is not like conventional cameras. We have a series of lenslets behind actually the main lens, and those lenslets, yes, actually capture
this. Equivalent, capturing images from different positions.
It's between the setting inside the API was 1 millimeter between each. Actually, each two images, each two views, horizontally and vertically. But it is some setting related to the lenslets.
I see. Yeah, do you think this baseline is sufficient for a light field display? Because for light field displays, you usually use camera array rather than planoptic camera.
Very good question. Very good question. So I conducted some geometrical, mathematical evaluation and analysis, which I hope to publish it later on to prove that some facts around your question. So it's not sufficient actually, and it's not clear to visualize it, and you need to mind some instructions if you want to visualize the planoptic contents on the light field display and to be appealing, actually to be noticeable and to acceptable. So yes, you're right, but it's not only about the baseline. It's about the size of actually the content, the position of the content, and the distance from the camera, the planoptic camera. It affects all these kind of things, affects for the perception, final 3D or light field perception of the content. I can say that only is the baseline. So many factors are affect to this clarity and this content final visualization.
Thank you.
No worries. Yeah.
Matthias. Yeah, two questions. One is if you go back to the distortion curves that you have shown.
For which data set? This one?
The last one.
This one or the last
Yeah.
one?
The other one.
This one?
No, the other one.
This one?
Yeah.
Yeah.
Do you have an idea why the performance of AV1 is so much better than VVC?
So this is a good question that I checked many articles related to that. Yeah, normally we expect that VVC should show a better performance in compared with AV1. But what I've done, I used the codes for all of these encoders, and for VVC I used the VVC DEC and VVC ENC encoders, actually, the formula or the...
Actually, that's it looks like, I was suspecting that you use VVENC, and maybe it's actually not suitable for the content.
Because the content, maybe one thing that affects these changes is that actually the frame was a quilted frame. We had some margins between each views. Maybe that affects the final quality, and this is the result that AV1 works better. But after all, I don't have any justification for this because I know that many tests are carried out and they resulted in VVC better than AV1. Yes.
I think there is a reason, because VVENC is highly optimized for perceptual quality of regular video, and this one is very special and very different because you have this.
That's the thing. Yep, that's one of the things that we propose in our paper. That's because of the frame. Maybe because normally whatever you see, even for high resolution contents, is a normal high resolution contents, and it's not like a quilted frames or this kind of things. Yeah,
I suggest if you want to test VVC for that purpose, then you might need to run the reference software, because that one just optimizes for mean square error, and it's more agnostic to the content. There's a similar thing that happens when people code like MIV or VPCC or things like that. And if they use VVENC, then the performance drops a lot because the codec is not suitable for this purpose. So I would not recommend to use it for this purpose.
Okay, thank you. Thank you for your recommendation. Thank you very much. Yep, I should analyze it later in more details. Yep, yep. Thank you.
Thank you very much, Kamran.
No worries, thank you.
It's very nice to see that you keep Lightfield alive.
Thank you.
Actually, I did exactly the same analysis. We published a paper on the efficiency of different codecs on the compression of the Lightfield images. So we saw a different behavior. So actually VVC was the best, but as Matthias thought, we used the reference software, both for VVC and for AV1 at the time. So maybe you can check it. But for me, it's very interesting to see if you could do the subjective test with your Lightfield display and compare it with the passive methods. Because for a long time, they convert the views into a video and they do this subjective test with that. So I'm looking forward to see this subjective test and your results. Thank you.
Yeah, we are due to carry out this subjective test. Thank you very much for your suggestion. Thank you very much. Thank you.
More questions? No questions. Thank you, Kamran. If possible, can you add the links to your data sets in the chat so we can add them in for
Sure. I will do that. Yeah.
Thank you.
Thank you. I stopped the sharing. Thank you.
So now we move to the presentation that Pablo and I have prepared on the status of the test plan that we are running. That's working. So, as you know, there is, I don't know how many meetings already. We are working on this test plan on immersive communication system and the evaluation of this kind of systems. So the idea of this presentation is to provide first a context to those that are not related, or don't know what we are doing, and then the status of the tests in the different labs that are involved in this test plan. The motivation of this test plan was related to some of us have already some systems by our own, and we wanted to know how to evaluate this type of communication systems related to immersive technologies. There were no recommendations out there providing some guidelines, so we thought about doing a test plan, evaluate different conditions, different systems, and then contribute to ITU trying to generate this recommendation for future tests. So the idea is to evaluate the effect of technical factors and quality of experience in these systems, and also be able to compare with other systems or other configurations of the systems. We looked for what was done before in other, not in immersive communication system, but in communication systems, and there were some recommendations already by ITU, for example, P920 on interactive methods for audiovisual communications, more centered on video conferencing, but they were providing some guidelines on how to test this type of communication systems. For example, proposing some tasks that were asked to the participants to perform during the tests so we can evaluate the technical factors. There was another one, P1301, subjective quality evaluation of audio and audiovisual multi-party telemeetings, also related to older technologies. There was this activity within, also from members from BQEC, the P1320 on quality of experience assessment and extended reality meetings, more focused on identifying the factors and constituents for quality assessment of telemeetings in XR. And they do not, they analyze the different factors involved in these scenarios, but they do not detail on how to evaluate them. And we also, Pablo and other colleagues, we performed some state-of-the-art review, and we published this paper on overview, taxonomy, and good practices to evaluate this type of communication systems. There's nothing in the chat. So we started working on this. We opened a work item at ITUT. This work item is PIXC, and this is a collaborative joint work between IMG and the study group 12 of ITU. We are working on the definition of this new recommendation for subjective assessment of extended reality communications. Our goal is to define a methodology that can describe the test design, including the inference factors to test, how to control the context, the human influencing factors, which quality of experience constituents to evaluate, etc. And the idea is that we can cover two types of design. One more, we call it systematically, so you have your own system and you can control on different parameters, and you want to test different factors of this system, or you go for a black box system and then you can explore other individual variables, so you don't have that much control on that. Apart from this methodology, we worked on identifying different tasks that we should ask to the people to perform during the test, so we are able to modify these technical factors and see how they influence on the communication. We identified 4 tasks depending on which component is more emphasized in the test. One for audio communication, that is based on the traditional tasks developed for testing telephony or video conferencing, visual communication tasks, or others on object manipulation, and others related to or taking advantage of the possibility to explore the environment in immersive scenarios. And then we try to identify a relevant subset of measures, especially working on questionnaires and on which factors we should measure in this test, and also not only on questionnaires, but also on analysis of behavior and different, probably physiological measures. So we are working on this. This is a diagram of what we have already mentioned. This is the methodology. So our hypothesis that some variations in some independent variable can have an effect on certain quality of experience constituents when a user execute or perform a communication task under some conditions. As you see, we can have these two branches, one for systems that we can really control every parameter, or systems that are more black box. And then we establish or define this context and the subjects, the tasks, the measures, and then we can provide an statistical analysis. So in terms of communication system that we are covering or that we are addressing, these systems should enable immersive, remote, and synchronous communication. So providing this sense of being in another place. You want to jump in with this?
Okay, yeah, so part of the work that we did on this paper was trying to create a kind of a taxonomy of the systems out there to be able to compare apples with apples, basically. The thing is that communication-wise, we kind of define that the key features that these immersive systems have are at least one of the three ones, which being able to have visual communication, so a realistic representation of the other person, or a realistic representation of the surroundings of the other person, like having remote presence on the other location, or representations of all the participants in a shared space, like in shared immersion. And it's for practical reasons, no system basically can cover effectively everything at the same time, except things that you can see in the movies. But covering one or two aspects is something that normally can be done, and it's a good way to figure out if you are able to compare systems which are oriented to similar kind of tasks.
Then we defined, or we started working on definition of these 4 tasks that are focused on deliberation. So we wanted to push or to motivate the conversation between peers, between the people that are participating in the test, normally oriented to achieving a common goal. Also, we wanted to target this exploration possibility that immersive technologies provide. So exploration of the environment and probably identification of different objects in the environment. And then also this manipulation possibility that we have in virtual reality, both with physical and virtual objects. And so it's related to the interaction with system elements and manipulation of objects. So we identified these 4 tasks. One is for audio communication task that is based on the survival task that was defined in a previous ITUT recommendation. I will provide some details later on. 2 tasks related to this exploration factor. One is on the visual communication task that is kind of performing a charade game or following some instructions from a professional. Then is this environment-based communication task that is kind of a treasure hunt. And in terms of manipulation, it's also based on an old standard that is block building. There was a task on Lego building before in previous standards, and we adopted this. And this is the set of measures that we have identified or we are working on, because it's something that maybe we have to iterate a bit. We wanted to evaluate the objective performance of the task, probably analyzing the task success, the time that you have to employ to complete the task. If the task allow it to evaluate the success rate or the user's error. We want to evaluate also the behavior. Probably we will do always conversation recording, so we can analyze the intervention, the time of speaking of each person. Also some, for example, movements of head or body depending on the tasks. Traditional subjective performance measures like MOS, ACR for video, audio quality or quality of experience. We can also evaluate delay or depth when there is some information related to this. Also other tasks, other questionnaires more related to simulator sickness factors or mental load. And then other more related to presence, quality of interactions or user experience. So we have identified some subsampled questionnaires from traditional questionnaires that are in the literature. So I'm going quite fast on this because we have already presented it, but if you have any questions, just let us know and we can go more into details on any of these aspects. So these are the participant labs that are involved for some months. I have grouped them on the different tasks that they are performed. So the three first, AGH, Ilmenau, and UPM. We are performing this more communication task, so more focused on talking, on audio component. There are 4 labs, CWI, Luleå University, Texas State University, and University of Surrey, that they are working on this more visual communication task, so following instructions from other people. Then we have 4 labs working more on this environment task, on the treasure hunt. It's Nokia, University of Padova, RISE from Sweden, and also a collaboration between Ericsson and University of Colorado Boulder. And then for the object manipulation task, we have 2 groups working on that, University of Roma Tre and UCL. So given the time restrictions, I have asked them, or we have asked them to provide us some slides with the status of each test. I will present them, but I think almost all of them are there. So if I'm not doing correctly, please jump in and correct me or add anything you want to add. So starting with these 3 groups working on the communication task, this is, as I said, based on the survival task. It was described in this ITU-T recommendation P1301. So the thing is that to put the participants in a situation that there is a hypothetical survival situation, and they have a set of objects, and they have to discuss on the objects and then rank these objects depending on the application for surviving this situation. We have modified a little bit this task. I will present it in another presentation why. And yeah, this is totally based on this. You give images to the observers of these objects, and then they have to talk and to discuss. On this task, AGH is working now, so still not started the test, but they have already 90% of the test procedure. We are, as I said, working on subtle modifications of this task. So they have thought about how to force this conversation for about 5 minutes between the participants, and they will ask about quality to each person after the full conversation. They are using a 2D normal traditional video conferencing system, and the software is almost ready. They will test 10 different network conditions. And 4 conditions will be related to audio only, and the other 6 will involve both audio and video. And they are open for suggesting interesting network conditions or simulating realistic situations. And all testers have the same network condition. So they are working on this, and probably they will start this test on September. There is TU Ilmenau also. I think Felix is there, but Felix and I will provide a more detailed presentation because we have already finished the test after this presentation. So I think we can go into details later on with Felix when he presents his presentation. And also in my case, I will present it later, so I will provide the details later. Second group of tasks or labs that are working on the visual communication task. There are 2 variants. One is charade, so a participant is given a list of words and the other participant has to guess them. Typical game. In this variant, the participants are seated and can move only their upper body, so they only have 3 degrees of freedom. And there is another variant on 6 degrees of freedom where a participant A is an instructor, for example, in physiotherapy training, who has to demonstrate some movements to a participant B that remotely has to repeat it. There are different measures of success, and we will provide some details also later. One group that is working on leading this task is CWI. Ashutosh is leading this. Please, Ashutosh, jump in if I am incorrect in something. They are working on evaluating the impact of latency and the synchronization in an XR communication system. The task descriptions, here are some details, but the basics are the same. So a remote person has to replicate or mimic the movements that a professional or a physiotherapist has to show. So there are some feedback on correct or incorrect exercise performance. There is guidance offered by this professional or confederate user for correcting exercise techniques, always thinking about forcing this communication among the participants. And to progress to the next exercise, you have to perform satisfactorily. The system factors that they are going to evaluate is latency that will be introduced in audio and video. And the objective is to find acceptable limits of these delay values for audio and video for smoother and immersive exercise experiences. They are using their system, VR Together, is based on point clouds, representations of the users, and you can check it in this reference. And there will be no encoding to these representations based on point clouds. And they are using, both participants will be using an HMD, that is the Quest Pro, that it's also provides some behavioral measurements. This is the test method that they are working on, and also with the different questionnaires that they are collecting: visual quality, quality of interactions, presence, cyber sickness, task or cognitive load, task completion time, and also, as I said, some movement data that can be provided with this HMD. The current status is that the system development is completed, the pilot tests are ongoing, and the actual test will be carried out in August. As you will know later on at the end of this presentation, our objective is to have the results by September, so all the tests are being performed right now. Another group that is working on this task is Lulea University. So again, the task is this physiotherapy task, as I have already described. The quality factors that they want to evaluate, or quality of system of service, is delay, jitter, and packet losses in this communication task. They will do tests with 30 users and one physiotherapist. The duration of each exercise is between 60 and 90 seconds, and the parameter settings are the round trip time delay, the packet loss rate, and the jitter. This is what they are modifying to evaluate the different technical factors. And the metrics, some questionnaires, very similar, because they have more or less agreed on which questionnaires to use, very similar to the ones that they have already mentioned on the CWI test. The tool to conduct the test is Altruist and NetEnt for network condition emulation. The current status and future work is they have already performed 88 tests, and they will finish the test by the end of August. Some preliminary results indicate that there is a strong correlation between quality of experience, video and audio quality, strong correlation on quality of experience and technology acceptance, and also they start to investigate quality of server bounds, of service bounds, and they will try to finish the analysis by September so we can provide more conclusions. Texas State University is also working on this task. They are evaluating 3 different systems. This is VRChat, Horizons, and Microsoft Teams. So 2 of them are immersive, and the other one is a traditional 2D video conferencing system. Again, they are using this visual communication task, not the physiotherapy one, but the charade one. So one participant has a list of words, and the other has to guess them. These are, again, the questionnaires. As I said, they have agreed these different labs on which ones to use. So the similar ones that they have already mentioned. And the status is that they have already performed the pilot tests and have started running the test with the objective of finishing after 4 semesters. And finally, we have also University of Surrey on evaluating the impact of packet losses on virtual reality screen-based teleconferencing. So the research question is, they want to evaluate how packet loss impact communication effectiveness when using a black box screen-based teleconferencing system. There will be 2 participants playing this charade game and 2 different setups, 2 VR systems, plus Teams versus Google Meet. They will modify the packet losses in the network and each one, the session how they are performed is they will last for 30 minutes. The progress is that the pilot test has been already completed, and the main test completion will be after summer. This is the test session also, and again, the questionnaires are kind of the same for the other labs, right? And these are some examples of the perspectives that the MIMER and the GESER has in this system. Okay, so we have talked about this audio-based task, the video-based task, and now we go to the environment-based communication task, that is a treasure hunt. You want to write?
Okay, so this is mostly focused on the exploration of the environment. This is especially targeted as remote support and systems, but not only. And the idea it is to have a repeatable task, so similar to guessing a word or the other task defined. So we thought about a treasure hunt task, which is systematically hiding objects or locations. I don't know if I have. No. Okay. So, but which basically means that in each step you need to navigate to a place, then find an object, then inspect the object, and maybe solve a hidden message, or basically the code with a coding substitution system. It is quite modular. You don't need to include all the elements in the task, but it allows you to simulate a lot of interactions. Basically, the different information that the people who's in the place and the remote people may have in each of the tests. So we have a few variants of that. This is the first one, that is the one that we have done in Nokia. So we are using an immersive telepresence system based on a 360 video that we have already presented. And so this is the situation of the test. So there's a local person with a camera that needs to find these objects and solve this and find some clues on these objects. And this simulates 3 different use cases in 3 different areas. So the telesystems, the museum, and the technical support in a very simplified way, which is the purpose of the test. So the whole idea is that the remote participant is the expert. This is it. He or she has the remote view of what's happening locally, and also some instructions like you need to find this painting, you need to find the horse head, and then you physically open the horse head because there's a window there, and you find the symbol, and then the expert has the alphabet to decode the symbol. This is how the test works. So this is the procedure, and this is the view of the remote one. You can also have, so we have 3 conditions. We compare with a baseline video call. We have this 360-degree video communication system, and we have what we call the magnifying glass, which is basically a smartphone that you can use to go closer to a part of the images and do a closer inspection, which helps a lot in the decoding part. And go for the next one. So this is we are rating a lot of things, let's say audiovisual quality, mostly in ACR scale, and some questionnaires regarding spatial presence, mental load, sickness, social presence, and quality of interaction, and also measuring the success rate. So we have had 9 per session, 3 participants each. It was finished. We hope it's enough to get some results. Otherwise, we might need to run a second try after summer, but still we hope that we can get some results. We are starting now the analysis of the data, and I don't know, we don't have any preliminary result that we can share yet. I can go on if you want. So this is one by the University of Padua, and the thing is that they are doing basically the same experiment, but in VR. So it's kind of similar setup, but with totally different conditions. It's both VR, and they're testing 2 different conditions. There's one which is the local, who's the one who needs to really have a look at the place and find the objects and decode them, and the other one which supports the local. And in one condition, the remote can hear each other and the remote can see in real time where the VR user is. In the other one, the remote cannot see where the VR user is. And this is an example of how things work. So there's a navigation part, which is more relevant in this task than in ours. So we can like see how the different technologies can be used with slight adaptations of the same task. And this is a test procedure. So there's a pilot study with 2 participants and the test with 30 couples of participants. And the recorded data, which is both the amount of network traffic, the location meter environment, and several questionnaires, which are basically the same or almost the same as in Nokia's test, so we can compare the results, and some analysis about they have like more analysis about the amount of interaction and audio semantics and the movement and success rate, and also of course the answers to the questionnaires and the impact of the transmitted content. I don't know exactly the status of what has been done.
They have already finished. They are analyzing that.
Okay, thank you. Because and yeah, this is the one being done in RISE. So it's basically we are karaokeing Shiring's presentation. So if we do it wrongly, you can jump it. So yeah. But I'm used to karaoke and all this presentation, not bad. So this is a remotely controlled vehicle, basically. So this is a single user task. We wanted that the test could also be used for these kind of systems where there's interaction with the environment, but not with other people. So yeah, this is the idea of the task, that the user can navigate to a target location and then inspect the location and retrieve, in this case, the traffic sign for the next location and then go to the next location. So in this case, navigation is important. There's no need to do the decoding part because there's no need to exchange information between 2 users. So in this case, we remove the decoding part. There are 2 view positions for the operator. There's a first-person view and the third-person view with the camera on top. And there's some support in using, so there's no second operator, but there's augmentation of data like text or help in visualizing the depth. And it's applied to the first person. So
yeah, this is more to show that it is relevant also for real use cases, right? So there are applications like, for example, in safety in airports where this remote control can be useful, right? And this kind of tests can help on how to define the conditions to manage these systems. And this is the questionnaires that you have been, or the things that you are mentioning, right? How would the quality of experience be applied to this remote control inspection? Independent factors is what Pablo has already provided. So one person, first person view or third person view with some augmentations, and what they are measuring is objective performance with eye tracking information, perceptor quality of experience, also asking for depth perception, socio-emotional factors like spatial presence, and also SSQ. These are 2 pictures of the demos that they show in Sweden last 2 weeks ago. And this is a video of the system doing the task. So going from one point to another, getting some information and moving for the problem. Cool. So last one of this part.
Yeah. The final one is the one being done by Ericsson and the University of Colorado Boulder. It is also nice because it's a different environment. It's mobile AR, basically mobile spatial communication, with the idea of enhancing the capabilities of mobile video calls, basically, especially when the people needs to share information about the location of the place. So have a collaborative exploration of the environment. That's the idea. And so basically the conditions to compare is the normal mobile video call with this augmented reality spatial call, where basically there's a 3D representation of the room, which is used to augment the quality of what's happening, of the communication. And the task is a variation of that, where two participants need to collaborate to find some clues about the suspect. So it's not exactly the same variant, but this is still quite related. So we are also using this research to compare with the rest of the research and see how we can introduce these insights into the methodology. There are two settings. There were two participants. I don't know the details. I believe that they finished the experiment and they're doing the analysis right now.
Yeah.
So they collected spatial presence, some spatial recall worksheet, and then some logs of the application and screen recording, and some structured interview. So it's, again, they came slightly later into the project compared to the other labs, but there's still an interesting collaboration because we can see other perspectives and other use cases and put their insights and the results into the recommendation as well. And they hope to have results by early September.
So that was all for the groups working on the environment-based communication task, and now we have only left the object-based communication task that is also based on an existing ITUT recommendation, the P920. That is based on block building. There was this, the original definition was based on using Lego blocks to build some figures. So now the goal is to perform a task that involves remote collaboration and in place the manipulation of objects. So there will be an instructor that will be able to manipulate a construction composed by blocks, and some builders that have to replicate the construction that the instructor is providing with the indications. We have two labs working on this task. One is Romatre, and the test conditions are, there is one user, remote user, that has a representation. Everything is in virtual reality in this case. The remote user has a representation of the target object and has also a supporting app for recording time. And he or she provides his instructions to the builder in VR. The VR user is in the virtual environment, follows the instructions of the remote user, and tries to build the figures. There are 3 levels of complexity for the blocks, for the figures, with different number of pieces. This is an example of the setup. So you can see the view of the remote user and the view of the VR user. I have to play this one. Yes. So the remote user, you can see it in your left. What is the remote user watching? He can see the VR user, how he's performing on building the blocks. And the VR user is in the VR environment. And also, as you have seen probably, he can see also the remote user in a planar representation of here like this. So different test conditions, both users can see and hear each other. The second one is only the VR user can see the remote user, but both users can hear each other. Then third condition is only the remote user sees the VR user, but both users can hear each other. And the final one is only they can only hear each other. 10 participants have been involved in the pilot study already, and 30 couples of participants have already performed the tests. They are finished, and the analysis is ongoing, analyzing the different questionnaires, surveyed users' motion in the virtual environment, and also conversational analysis. And finally, the last lab is UCL, and they are also working on this block building task in an environment, also virtual environment, that is a 3D model of an office with different objects. They are virtual cubes, of different sizes and colors, again with different levels and different depending on the number of blocks. Also the selection technique, there are the seek and grab and the building technique. There is no gravity on these objects, and but they can snap to the cube to the target. So the experimental protocol, I mean, they are using Ubiq WebXR. Ubiq is an open source tool developed by themselves where they can set everything, all the parameters. There is one confederate participant that is the instructor that can see a representation of the figures and give the instruction. And there is another participant in VR that is the builder that follows the instruction of the figures and the conditions. There are 4 rounds, so there is no observer and no sound feedback, no observer with sound feedback, and then observer no sound feedback and observer sound feedback. So different combinations of this. The metrics that they are gathering: task completion time, the speaking duration, and some behavioral measures that are logged on with this app, with this Ubiq application, the head and body position and rotation, the body position and rotation, where are they looking at, and the objects that they have grabbed. And the question is, what they are evaluating is, again, presence, co-presence, social presence, and enjoyment in this case. Status, they are recruiting people for the pilot test. In fact, they are going to use our summer school that is next week. This is publicity. And they are doing an online recruitment. So since they are using this web-based application, the test will be done remotely. And the full study will be during the last weeks of July and the first weeks of August. So that was the recap of all the tests that are.
Small comment about this task is that there was also an experiment already done between UPN and CWI, which of also Lego block building with CWI VR Together system and cooperation between 2 people that is kind of not actual part of the test plan since it was done before, but quite well aligned to that. So we are probably using
the seed of the.
It was kind of the seed of this particular task. So it also will be, I mean, the results which are already published will also be used as part of the contribution to the recommendation.
So the steps, we want to finish all the tests by September. In September, we are planning to have an IMG meeting, probably in person in CWI in the first week of September, hosted by CWI. We have also some things still to be discussed. For example, agree on the terms of sharing the results and the data, especially in terms of GDPR and privacy. So we have to agree on some of the content on the consent forms and some privacy issues that have not been addressed yet, and we will probably address them in this meeting. The idea, as I already said at the beginning, is to write an ITU recommendation. The deadline for this will be to have.
We had a draft.
We had a draft. This is a copy-paste error that we made.
So we had a very simple draft last April. The next site study group 12 meeting is in January, and we hope that we can have, ideally the recommendation written for consent by them. But let's see. Otherwise, at least a much better version, so that even if it's not ready for consent, at least it can be discussed and consented in the meeting after.
Regarding the results, our plan is to present them in the next plenary meeting, and for sure work on a joint paper with the whole test plan, and also each lab is exploiting the results or their experiments as they want, and some of the tests have been already published. So, I think these discussions will be done in future audio calls and in the small group, but we are welcoming any comment or any questions that you may have.
Yeah, before that, maybe something about the recommendation as well is that we probably, so we are having this IMG meeting in September. I mean, tentative this is a place and location. It might change, but we will have the meeting. This will not change, and we will probably do we try to do a bit push of the recommendation writing or kind of agree on what should be included in the recommendation, and then probably kick off some editing calls on a bi-weekly basis. We tried to do that for the April deadline. We were well successful enough to have a draft, but not much more than that. But still, we decided to stop the edition of the document until we were really able to have some results, so that we can really know what's working and what is not working. So the idea that first we decide what should be in the recommendation, and then with that we write. So there will be hopefully a writing effort starting in September.
It was just a quick question about the agreement for sharing the results. I don't know if because at times it takes a while, especially if you're trying to get institutional agreements to get this. So I don't know if we would still be able to meet the deadline for January or something.
So this is something that we have to discuss. I don't know. This came also especially because, for example, we completed already the test and we followed our normal methods. But for example, CWI had some restrictions on and required some approvals from the institutions to do tests, and they were asking for an agreement on this, especially on sharing the results. So I think it's probably the best thing would be to try to know what we need each other in our institutions to reach this, and then put everything together and try to be to reach an agreement on this. So for the previous test plan, we already put in the recommendation a draft of the consent form and everything. So, but in that case, there was no behavioral data or some things that are more delicate. So probably we have to think about it in the next course. More questions or comments?
Yes, I have a question about the IMG meeting that is going to take place in September. So it's final. These dates are final now.
So we can say, I don't know, because I did a form or a poll to know if people agree with these dates. I did it not very good, so I don't know who said what thing. So I know that there are people, I think there is 9 replies to that poll, 6 of them are attending and 3 are not attending. So maybe, I don't know if we are all here or at least one person from each participant lab. For us and also for CWI is the best, I think, I should just correct me if I'm wrong, but is the best option.
Yes.
But I know that people from Roma and Padova cannot join, but I don't know for the others. Alex, I see your hand.
Yes, thank you. Yeah, I mean, principally the week is actually pretty good. Just the starting day is a bit suboptimal, at least for me. We will have the Q14 interim meeting just the week before in Sweden, and it makes it a bit hard to basically continuously travel, more or less, if you want to go from Sweden to Amsterdam. So maybe could we start a day later? Would this be possible, like 3 to 5th or so? Or is this absolutely not possible?
I mean, this proposal came, in fact, because I'm the limiting thing is it's me that I start classes on the 5th, and I have classes from Tuesday to Friday. So it's difficult for me to find another week also. No? I don't know if we need 3 full days. So probably, I don't know if we can go for 2 in the afternoon until the
okay, that would work. I mean, if we started maybe at lunch or so, then maybe it's possible. Yeah, okay, that sounds like a good idea. Yeah,
in the morning, we can travel in the morning of the 2nd of September, and then I think 2 days and a half should be enough. Sarah, please. Hello.
We cannot hear you, Sarah. It's very strange.
Sorry, can you hear me now?
Oh, yes.
Yeah.
Okay, I'm sorry. So yes, as you said, from Italy, we have like a meeting of the Italian telecommunication group, but I think that if needed, we can be able to split so that some of us attend the Italian meeting and some others join you in CWI.
That could be great, yes, that could be very good. So then if we can agree on this, maybe we can fix the dates and we start the second, I mean, after lunch, and we finish the fourth in CWI in September.
I mean, I'm also, if you can travel on Monday morning, it also saves some family points for me as well.
I mean, it will be very specific meetings.
Yeah,
I don't think we need 3 days, 3 full days.
It's also better for.
And I have a question.
Sure.
Okay, yeah.
Yeah, I saw that some of the labs have a plan for conducting experiment during September, if I'm right, including us. And as you're going to discuss the results, what would be the point for us that probably we will not finish our experiment by this time?
So I don't see a big problem if some experiments are not finished, because I think they can be added to the recommendation. The point for these labs to attend may be especially if you're interested on helping on writing the recommendation, because some slots these days will be devoted to do like a writing session on that. So even if you don't have the results, at least you have the methodology, you have probably some preliminary results or some ideas. So it would be helpful if even if the tests are not finished, to have it there.
So for some of the inputs to the recommendation, being able, especially if we want to test the metrics, being able to have some numbers and see if things react to the metrics or not, is nice. But for most part of the thing, the work so far, so having, like prepare the method, prepare the system, and all the qualitative information that we have gained on this work is probably the most valuable part towards the recommendation. So all the work that you have done, in particular achieving, being able to, put the experiment running in a few conferences and testing it with people and stuff, even if you didn't ask the questionnaires. I think this is probably very valuable for the contribution anyway.
More questions, comments? Okay, if not, we can move to the next two presentations before lunch. Felix, are you there? Do you want to start yourself?
Yes, I'm here.
These are related to this test plan. These are TU-Ilmenau's tests that have been already performed, and then I will present the ones that we have performed in UPLS. So go on, please, Felix. You can share your screen.
Sure. I hope you can see my screen.
Yes.
Okay, great. Okay, thank you, and welcome also from my side. My name is Felix Immer from TU Ilmenau. I'm presenting today on the subjective evaluation of the impact of spatial audio on triadic communication in virtual reality. This is collaborative work together with our project partners and also in context of the WCAG IMG CrossLab work plan that was just presented. I would like to start with a brief motivation. The audio or auditory presentation is just one of many factors that can affect experience in such multimodal immersive communication systems. With spatial audio, it has been shown that it's generally preferred in listening situations and also shown to elicit a positive impact on cognitive load, speech communication quality, and also overall quality of experience. In conversational situations, for example, in video conferencing, and it has also been shown to increase the perception of interactivity, shared space, and ease of understanding. When transferring that into the context of immersive systems, like social VR, for example, typical quality indicators also include the concept of immersion and social presence as the impression of being together and in social interaction with another person. Spatial audio has been shown to lead to higher immersion and audiovisual quality in single-user VR. However, in immersive communication studies, while they show relative that they can elicit a high social presence, they typically do not consider spatial audio and exhibit an overall rather low scene complexity. Hence, in this work, we focus on conversation studies and multimodal VR, evaluating the effect of spatial audio on social presence, aspects of plausibility, and communication behavior. This is actually part of a series of studies. So we started with a proof of concept study in a dyadic situation. Then in a second study improved on method and task in a collaborative dyadic scenario. And now a scale towards higher communication and acoustic scene complexity by conducting a study with 3 simultaneous participants, so a triadic negotiation scenario. In this study comprises an interactive audiovisual communication test with 3 simultaneous participants. The independent variables in a within subject design include the oralization method, comparing a dyadic non-spatial to a binaural spatial audio representation, and comparing that to a real-world face-to-face reference condition. The dependent variables include social presence and aspects of plausibility that is typically assessed to questionnaires. Specifically, we used the Network Mind Social Presence Inventory, or 3 subscales of this, and a second questionnaire focusing on aspects of plausibility, including coherence, task, enjoyment, interaction, and also aspects of quality. As an outlook, there's also we also collected tracking and speech recordings. We plan to do also verbal and non-verbal behavior analysis. The task that was used in the study is based on the survival task from originally proposed for traditional telemeeting assessment in ITUT recommendation P1301, in which participants are placed in a fictional survival situation with the goal to select and agree on 6 out of 12 items that are important for the group's survival. The task in our case was limited to 6 minutes. Now here we adapted this task in a spatialized version, specifically for the room scale social VR study we planned, in which the survival items are represented as boxes distributed in the room with the goal of the task, the scenario description, and the survival items unchanged from P1301, but with updated imagery and distributed in the room. This is how the scene and the virtual environment looked. The items are distributed in the room as manipulable boxes, and the scenario description is also part of the same room. In the center of the room, there's a shared and marked space for decision making of the group. The system we used is based on a framework for conducting and analyzing social VR studies developed in collaboration with our project partners. And the basis of this is a Unity application where each participant joins through this application that are connected to the Photon Unity networking service and Photon Voice to share scene state and audio. The binaural audio rendering is realized with an extended version of the open source PyBensem renderer. Experimental control is realized with the BML-Tux framework, and we also realized recording of the full session, including tracking and speech with a Unity-based plugin. For hardware components, we realized a wireless setup with Meta Quest 3 and Airlink mode and a set of analog audio transmission equipment. The audio rendering was realized with BiBandSim, while the direct sound was dynamically synthesized based on head-related transfer function datasets. The reverberation was based on a measured set of binaural room impulse response measurements from the lab rooms we used for this. The reverberation in this case was not position dynamic, since the approach has been shown to elicit an impression as plausible as an entirely measured binaural room impulse response set. Here are some impressions from the study, and on the left you can see the wireless VR setup. In the middle, the virtual representation of the survival game scene, and on the right, a matching real survival game scene representation with the same elements, the boxes, the scenario description, and shared decision making space. The study was conducted with 66 naive participants, 42 male and 24 female participants aged 21 to 38 years, while 47 participants reported to be unfamiliar to each other. 19 were familiar or reported familiarity as colleagues, classmates, friends, or family with their respective conversation partners. From the study procedure side, after training phase, there was a short setup phase for putting on the equipment, then performing the conversation task with a subsequent questionnaire outside VR that was followed by a short break. And after all trials have been completed, there was a short exit interview and a preference rating of the ranking of the three subsequent runs. For the results, we looked at social presence, namely the NetworkMind social presence inventory as a questionnaire. We used a reduced set of 16 items that are 3 subscales of the NetworkMind social presence inventory, namely co-presence, perceived message, understanding, and mutual assistance, all rated on a 7-point Likert scale. While it can be seen that face-to-face significantly outperformed VR, there is a trend towards spatial audio performing better than the non-spatial audio case, but there's no significant difference between the 2 oralization methods for social presence. For the second questionnaire part, it was based on aspects of plausibility with subcomponents for coherence, task, enjoyment, interaction, and quality. In total, a set of 12 items, also rated on a 7-point Likert scale. Here are 3 exemplary items displayed, showing the same overall trend of face-to-face or the real condition outperforming the VR condition, but even in a question focusing on the auditory representation, in this case Q3, the environment sounded convincing. There is a slight trend, but not a significant difference between the 2 oralization methods in this scenario. After the experiment, the participants were asked to rank the 3 runs by condition number, and from that I compiled these 2 plots for condition and scenario preference. It can be seen that face-to-face was most preferred and non-spatial audio was least preferred. However, the difference is maybe not as clear as expected for the 2 oralization methods. The scenario also played a role, but not in a significant way. There are some limitations to this work, including the evaluation method, since we used very holistic subjective metrics like social presence and plausibility that didn't show a significant effect, although psychoacoustic changes are existing. Also, with the questionnaires and the high number of items could be problematic, especially within subject designs with repeated questions and potential questionnaire fatigue. And it has been shown in listening tests that listener expertise plays a crucial role, but we used naive listeners, which also could have an effect here. There are also some technical limitations. For example, the limited acoustic scene complexity, since it was a triadic situation, but still in a relatively low reverberant room. And the user representation, the avatar, were abstract, not realistic, with a limited tracking of expressions and nonverbal behavior, potentially also limiting the effect. The task, although it was highly social, it also might exhibit a high cognitive load and focus attention on many different aspects away from rating specific parts of the environment. So that could also be a limiting factor here. In summary, we designed and conducted an interactive multi-party VR communication study and implemented a task that was adapted from traditional telemeeting assessment for social VR in a spatialized version, encouraging spatial exploration in the scene or movement. We investigated the impact of oralization method on social presence and plausibility. And while face-to-face was rated significantly higher, spatial audio showed a tendency for improvement over dyadic presentation, however, no significant effect observed on the subjective metrics so far. This might potentially be limited by dependence on the scenario, including task and overall complexity of auditory scene and the communication complexity. In the future, we plan on extending on the evaluation, namely with verbal and non-verbal behavioral analysis, and in subsequent studies, further increase complexity, both communication and acoustic scene complexity, for example, in a group-to-group scenario in reverberant rooms, where we also investigate the effect of visual factors, for example, different kinds of user representations, realizing a combined high audio-visual quality, not only auditory quality. And in this context, also assess the influence of physical co-location and simultaneous reference to a real-world counterpart in the same moment. And with that, I would like to thank you for your time and attention.
Thank you, Felix. Questions for Felix? I have one. Thank you, Felix, for your presentation. We discussed the results a lot in Pomex, but I have a question about the system where you presented which is that you are, if I understood correctly, you are rendering the binaural representation outside and then sending it to an analog headphone. So is there any, I guess that the reason is because there's no way of doing it directly in the HMD, but I was just kind of wanting to confirm, and if what you do is similar or different than what you can get by kind of a standard Unity plugins or stuff. So a bit, elaborate a bit on that, just for my information, because it's very interesting, but I don't know too much about this.
Sure. Thank you for the question. So we realized the audio reproduction with this PyBandSim rendering tool. That's actually a Python application that is running outside Unity, and there's a custom a Unity spatializer plugin that sends scene information and also the dry microphone signals to this PyBenSim server on each client side. And that is then played out through an audio interface that is connected to a set of wireless equipment, and we use analog equipment for basically to ensure it's latency free. And yeah, it is the reason we do this is that it proved a challenge to bring this rendering technique onto the HMD itself. And the recording of the scene and the speech is also handled in Unity. So the transmission between the clients of the dry microphone signals also realized with Unity and the Photon Unity networking service. So everything needs to go through the PC application.
Okay, it's sorry. Thank you. It's wireless, but it's actually rendered by the PC and using Erlang. So you are not using like Android application. It's Unity in the PC plus Erlang.
Right. Exactly, but Erlang is not handling the audio part, but the wireless equipment connected to the audio interface that is connected to the Unity application.
Very, very nice. Thank you very much.
Thanks.
More questions? Okay, thank you, Felix. Then the last presentation is mine. I will try to be fast and on time for lunch. So this is another test that is under the scope of this joint test plan, what we performed at Universidad Politécnica of Madrid with one of our students. So the case study that we were evaluating is the impact of display techniques using a free viewpoint video system that we have there at UPM. So the motivation, as before, how the technical parameters of, in particular, this system called FBB Live impacts the quality of experience of the users during a communication scenario. And in this, I heard something? No. And the first study that we conducted is the impact of the display technology. We have, I will provide some details. We have two rendering methods. One is using a 2D screen, and with a joystick you can navigate throughout the scene, and another display technology is using the HMD, so you can explore the scene that is captured with the free viewpoint video live system. So this is the FBB Live system. It is consisting of now a setup of 9 cameras located in this array that you can see in this picture there. It is consisting of cameras, I mean low-cost cameras, let's say consumer-grade cameras, and the main advantage is that this system works in real time. To the original system implementation for this task, we added bidirectional audio, so we can communicate with people being recorded within this free viewpoint video system, and then with a remote user. And also people that will be recorded within this scene will see a representation, a 2D normal representation of the remote user. So there will be bidirectional asymmetric, but bidirectional communication. As you can see in this video, you can see the mobile phone is another rendering technique or another display technique. You can explore the scene. There is kind of 6 degrees of freedom, so you have horizontal movement. You can also go into the scene and go out. And as I said, the other 2 techniques that we are testing is the HMD. So you can see this a scene that is recorded with HMD or a 2D big screen and then navigate with a joystick. So the experimental setup, we did some pilot sessions. We tried, as I said before, with the survival task, we tried to define some specifics of this task that was already or originally developed for telephony conversation. So we tried to figure out how this is going to be working. Together with AGH, with Kamil, that helped a lot on this. We performed some pilot sessions in face-to-face situations, doing the survival task, to analyze some timing, how people is discussing, or if we have to limit something or not. At the end, we modified a little bit the survival task. The survival task, the objective is to rank these objects that will help you to survive in that survival scenario. In our case, in order to promote more the discussion, we are asking the people to discuss and then select the two main applications of the objects to survive in that scenario. We at the end, we set up 4 hypothetical life and death scenarios, 5 objects that can help the group to survive in that situation. There is a first phase of individual thinking, so they are provided with the instruction, the scenario, and the objects, so they can think about what are the applications of these objects. And there was a limited time for the discussion to 6 minutes. This was even shown with a timer. Okay, so the test session was not super long. So we have 4 scenarios. I said that there is what is in Spanish, but we provided a description of the survival scenario and then some pictures of the objects as it is recommended in the US recommendation. And these are the environment and the equipment that we use. The local, or what we call local, is the people that is being recorded by the FreeViewPoint video system, as you can see in your left. And they are sitting in a table. They have the pictures of the tasks, and they have also the instructions. And you can see there is a Jabra speaker, so they can communicate with the remote user. And also you can see a screen somewhere there where they can see a 2D representation, I mean a video representation of the remote user. In the remote part, so it's here we have the 2 conditions with a 2D screen and a joystick to navigate through the scene. And also using an HMD, it was an HTC Vive. In total, we had 54 participants. They were groups of 3, as you see. 2 of them will be placed in local, and 1 will go to remote. So the test session is, there is a first scenario where all of them are physically in the same place, so it's face-to-face scenario. And then in the other 3 scenarios, 1 of the persons will go to remote, either to the screen or to an HMD. After each scenario, they will have to fill a lot of questions in a questionnaire. And this is what we evaluated: overall quality of experience, audiovisual quality, communication easiness, social and spatial presence, quality of interaction, subjective performance in terms of the sense that they have of being able to perform the task, and also satisfaction with the discussion, and then cyber signature and task load. And also we recorded the conversations so we can have some analysis on the time spent talking each of the users, etc. So these are some results. In terms of system performance, they rated the quality of experience, the overall audiovisual quality, and also how easy it was to communicate with the system. We can see you can see the different bars. The blue one is when they were everyone in person. The orange one is for the participants that were local, and the gray and yellow one is the responses for the participants, the remote participants, depending on if they were using a screen or an HMD. As you can see, the HMD it has lower quality of experience, especially influenced by the audiovisual quality. This is because this setup, I mean, normally the HMD provides lower resolution and lower audiovisual visual quality than a 2D screen. And also in this setup that we tested was not the final version, or at least the better version that we have now. It was a preliminary configuration, so we were expecting that the HMD will perform, or at least the quality of the HMD will affect it. So this is something that we were expecting. Also, in terms of communication easiness, there is not a big difference. What we found out also is that this task may be not very suitable for testing the added value that can provide an immersive communication. You just need to talk, so probably you don't need an immersive representation of the remote users. And people may be more used to use normal 2D screens and normal communications scenario. So this is also the way we expected the HMD would be worse. In terms of quality of interaction, no big differences between HMD and the screen. So these quality of interaction questions were related to how they felt connected to the partners, if they were able to understand the messages, etc. In terms of spatial presence, we can see some lower results in the spatial presence using the HMD, no big differences in social presence, although in one of the questions that was if they felt present with other people in the video, this was the HMD was lower. As I said, I think the configuration and also the quality of the HMD can influence any factor that we can test here. And in terms of the subjective performance, so the general satisfaction with the discussion, or if they thought that they completely completed the task correctly, no differences also among the four scenarios. No problems with SSQ or with mental codes, mental load in general. And in conclusion, what we wanted to know is methodology more or less worked because we got at least in system evaluation where we expected that in this case HMD can be worse. In terms of task, as I said, the main component is audio, so immersive solutions may not provide an added value in this, and this is why we see better results for 2D against HMD. So we are working on possible improvements, and maybe we will do another round of tests also with the other labs, trying to make the task more attractive, maybe introducing some gamification things, or at least providing a clear impression when you are doing it right or not. This time restriction that we have imposed of 6 minutes is not also very ecological, so we wanted to provide a task that is more or less limited in time, but not that specifically. So carrying a discussion is not very pleasant. So there is probably we can add more need to look to the objects, so we'll increase the visual component of the task, and probably we will be able to better evaluate visual factors of these systems. Future work, we will test this system with other technical elements, not the display technique. So in this system, in this preview point video system, there is a compression of the color information, but not the depth. So we are working on testing different depth compression methods, view synthesis methods, and also latency in the communication, and probably also use other tasks of the ones that we have already described, like charade or block building in this scenario. So this is all. 1 minute past the time. So any question?
What kind of 3D rendering technique did you use? That was like, is that point clouds or
it's color plus depth, and then in the transmission, maybe Narciso, you can provide better details.
IDR, we have the main cameras. The main cameras, each one deliver 2 streams. One stream is the texture, and the other is the depth. But each camera is a stereoscopic camera from set, the fixed baseline. So we compute the depth, and we have therefore 18 streams, and on the synthesizing virtual machine, because it's a virtualizer function, takes the 3 closest streams. So we are switching between streams to reduce the bit rate required for the transmission. And within this stream, we created the IDR with the virtual position. And the virtual position can be defined as was seen there, just with a hand or with a game controller, or just based on the headset located on your head. So we are able to synthesize the image using 6 degrees of freedom. That is,
I see. But
in real time, roughly the end-to-end latency is between 200 and 250 milliseconds.
Google has this Starline paper with brain arching. So it's kind of similar input, but I'm not sure if you're
But we were interested in obtaining a real-time process. So we are looking for lightweight algorithms that allowed us, I say, from capture to delivery, our ability to display the synthesized image is between 200 to 150 milliseconds.
They can do it.
So also here, what we have a motion to photon latency is just 1 frame, because each frame is computed with the last parameters that we are receiving. So it's just 1 frame or 1 frame and a half, depending on the retina.
Well, I'm also curious how much time, because you had a lot of questionnaires.
Yeah.
How much time did
So the total
on
questionnaires, I cannot say. On the total, it was less than 1 hour and a half, but there were many questions. In fact, this was one of the objectives of this preliminary or first study, is to check if it makes sense to do all the questions or not, or we can just take some of them.
So sometimes we definitely fatigue questions.
Yeah, sure.
Questionnaires. And sometimes it's just good to ask, how to make it better.
Sure.
If you had to make it better, what would you change?
Maybe it's in some cases it's better to get some useful feedback to just ask like open questions and then do later on some qualitative analysis on the responses. I agree with you. More questions? So thank you, and with this we close the session, I think.
Okay, I guess we are on lunch break. So I mean it's just 4 minutes after, so we can go after the schedule. We'll be back here at 1:45.
We will be on time.
Yeah, we'll be on time.
Just we are going for the group photo now in front of university, so it would be good if all of you could join.
Have the photo now or
no, and then we go from there to
Mensa.
Just a start.
Okay, so welcome back. We have a last presentation related to IMG Group. And this case is Stefan Fremery, from TU Ilmenau, who will present this work. Stefan, are you there? You are sharing already?
Hello. Can you see my screen?
Yes, perfect.
Perfect. Okay. Yeah, thank you for the short introduction. Today I will present you AVT EcoClass VR. This is a data set for audiovisual 360 video and immersive CGI data set to evaluate cognitive performance. To motivate this thing a bit, at first, what is cognitive performance in this regard? This means, to evaluate how children and also adults are performing in tests. Let's call it tests, little tests in the lab or in school somewhere. And we want to investigate this especially for classroom type settings. And to do that, we want to increase the realism of these procedures in terms of as well the tasks used and also the representation. Usually, the existing test paradigms look like that. Person is sitting in a relatively clean environment and watching at these mostly not so immersive type of contents, and then rates something. And we want to transfer this to immersive virtual environments using 360-degree video technologies and also CGI technologies, and then adapt this to audiovisual paradigms, actually, with also appropriate audio representation. So this is our goal. The background behind this is that, as already said, it's mostly simply done, like, for example, here, this is already VR, as you can see. This is a paradigm from Arons et al., which is the basis for our implementation, actually, or the basis in terms of the paradigm, at least, where you have arranged speakers around the listener. And then your task is to detect which person speaks which story about which topic. So this is to bear in mind always the task. And this was done here by some kind of color to person mapping. And just to highlight this here, Yeah, as already said, visual aspects are often overlooked, and we want to transfer in total in the project 3 auditory paradigms. But today we'll just talk about one, which is called audiovisual scene analysis. We want to evaluate this paradigm today, at least a bit, and then develop some kind of cognition-based QE measures in future, and also investigate the impact of technical aspects of IVEs on cognitive performance, which we also will have a short look today. But today we mostly talk about the data set, which has the objective to validate the suitability of the paradigm for cognitive performance evaluation. And the method we use is subjective testing mostly. The setup of the paradigm was transferred to IVEs, that it's a bit different. We have now a circle of 20 chairs with 18 degrees of steps in between. We have 2 scenarios, 360 video here and CGI at the bottom, with 3D scanned persons. And the task in this subjective test for the subject was to assign the stories to the speakers as quickly and as accurate as possible. The procedure was done with a self-developed interaction wheel and array to assign these symbols to the input fields. We will see a video later on how this is exactly done. And each story plays back for 2 minutes, and then the scenario was exited, or subjects had the possibility to exit it before themselves. They had a break if needed afterwards, and then there was the next scene. Now to come to the production steps of the 360 video pipeline, how this whole data set was created. We have 20 speakers recorded in our virtual studio, actually with the Insta360 Pro 2 camera. We also recorded a 360 image with this same camera, and then we captured the audio with the close talking bow microphone. And in total, this resulted in the following steps here, in this following pictures. For stitching, we had used the stitching software of Insta360. We did some AI denoising also to enable the chroma keying be better done by DaVinci Resolve. And for the implementation, we have used Unity and especially the video player component, and developed this story to speaker mapping input system. And for the spatial audio solution, as it is a collaboration project between RWTH Aachen and RPTU Kaiserslautern, we have used their software, actually, Virtual Acoustics, to do that. For the CGI scenario, the steps have been a bit different. So after the single recordings in our virtual studio, we had done recordings with the 3D scanner, the Artec Leo, in our labs. Did some data processing with the proprietary software of Artec Studio. Arranged the 3D models a bit, had done some rigging to make it possible to animate these avatars also. For the later implementation, we had used SketchUp to design the classroom, as you can see here in these 2 images in the bottom. And for the implementation, again, Unity, and the same things actually as for the 360-degree environment. The whole data set, you can download it either via the QR code. I also post a link now in the Zoom chat. And it consists of 20 different speakers in German language. And in total, because we have 10 stories plus 1 silent condition where people didn't speak actually, this led to 220 different video recordings, and also the 1 360 image of the classroom. We have the 200 single channel audio recordings, the rigged 3D models included, and 3D scans of these speakers. The 3D model itself, the SketchUp model, 360 manipulation and CGI implementation in Unity, and also example output data from the currently conducted subjective tests, where we had 5 subjects for both IVEs included here. And this is how it looks like. Actually, for the 360-degree video IVE, the stories are played back. And then as you can see here, the people had the task to find the correct speaker and map the correct story now with this input system to the persons. This was the 360 scenario. This is how it looks for the CGI scenario. Actually, we had the idea to implement it in a way that it looks kind of comparable. For the evaluation, we have done 3 subjective tests where the task of the people was to assign stories to speakers using the interaction wheel and ray, and also answer quickly and accurately. While we had the presentation modes, as I already said, and actually also different audio conditions, mono audio for the first experiment and also 360 video for the first experiment. And then for the second and third experiment, we had binaural free field audio condition. And for the second experiment, actually also 360-degree video. And for the third experiment, CGI, actually. And data management-wise, we saved the story-to-speaker mappings in JSON files, and the viewing data was recorded in CSV. This means like head rotation data or so. And this is one results slide actually here. Mainly this talk should be about the data set, but here you can see some first results of our studies. So on the left side, you have the results for 360 video and mono audio. What you can see here on the x-axis, you have the total number of stories presented to the listener at the same time, actually. Yeah. And on the y-axis, you have the correctly assigned stories in percentage. So as you can see here, for mono audio, it is pretty hard for people to correctly assign the stories. It works up to a number of, let's say, 4 stories at the same time. But after this, the performance really decreases. As you can see here, for the same visual condition, but binaural audio, so people really hear the speakers from the directions they were sitting in the circle of chairs. There it's really working far better than for mono audio. This was expected, but we didn't expect this influence to be that high, because it works quite fair until, let's say, 7 to 8 speakers at the same time. And for CGI, one can say this is some kind of in-between scenario, because as you maybe have seen from the video before, there is no lip sync. Yeah, so for 360 video, you have the advantage to use lip sync to at least have some kind of relation who speaks. For CGI, you just need to use your head rotation to find out who speaks actually. And there you can see that it's it works quite fair until 6 or 7 stories or so. Yeah, but not as good as for 360 video, where you in addition have this lip sync and the matching, the visuals matching to the audio. Okay, that's it for now. Just some very short slide about the total time spent. We spent a lot of time to summarize this, mostly for rendering, but also for development, of course, and so on. Just to see these numbers here in comparison, the 360 video IV was really time consuming. CGI is a lot easier to implement. With this chroma keying for 360, it really took a lot of time and also adjustments and lessons learned, let's say. And we created a relatively big data set with 3.7 terabytes in the end. So here is a link again with the QR code and a bit bigger if you want to download it. Actually, just a summary of the data set again. And in future, we want to also conduct further subjective tests with these both IVEs we have developed and further investigate factors like lip sync, video resolution, or more on cognitive performance. Yeah, thank you very much for your attention, and I would be happy now if there are some questions, then I can answer them.
Thank you, Stefan. Questions for Stefan?
I'm not an expert in audio, but I wonder what are individual variations in the localization when you provide binaural audio. So are there huge enough differences in how people are capable of actually using that information?
Yeah, actually, there are more differences for the CGI scenario in this regard. So for 360 video, it's better because people seem to be experiencing this a bit more like they would experience it in a real situation, I would say, because you have the lip sync and so on. But with the CGI, it's really, let's say, more kind of not a game, but it's more like depending a bit on what subjects have done before and how good they are at doing this. Yeah, this mapping with the direction of the sound coming to the respective person. This depends a bit on other factors than, for example, like I think also physical factors, how well people are able to locate sound, maybe also. I think there are quite some differences. Yeah.
Thank you. More questions? Questions from people in remote? Doesn't seem so. Thank you, Stefan.
Thank you.
Close IMG, I think.
Okay, yeah, good. Would you be in mind also enter some of the notes into the
minutes,
edits from your session?
Sure.
So, yeah, I think we should have an admin session now. I'm not so sure how far we can get. Margaret is not available, so most likely we will follow up with a audio meeting with the board after the summer. But maybe we can have at least some let's say opinions to start with. Which, okay, I'm not connected anymore. Okay, just a few, let's say, loose notes here. So usually we have had in the autumn a online meeting. It has been mostly the last few times in December. That could also still be a good option. But if anyone knows about any competing event November, December, that might affect the replacement of the.
VCIP will happen.
Pardon?
VCIP will happen in December.
VCIP?
VCIP.
And when is that?
That's one.
December 8 to 11.
Anyone here that would like to host the online meeting? Usually also need a host for also the online meeting that is quite lightweight compared to making this type of meeting, but we need to make sessions, Teams, Zoom, and set it up and then communicate the links and so on.
I could volunteer as long as I'm not going to China again. Yes, there is a chance I will be, because Lucian can make it probably from the US, but I can make it. If I'm at AGH, I can make it. But it would be good to have someone as a backup as well.
Okay, yeah. I mean, I put question mark here, so.
I'll probably know around September. No.
Okay, yeah, that's early enough, depending on.
Yeah, I have no control on that. Besides that, I can arrange it.
I could do a backup if needed.
That will be University of Aachen.
Yes. If you want to, you can put RWTH. RTVH. It's not something you can do. H. Perfect.
Is that kind of a department or a lab or?
So that's a university, and the lab would be image processing, which I think that's fine.
If you say ADH, the equivalent is RTVH.
Okay, I get it. Okay, thank you. So, yeah. Any other competing event that you know about? One factor here is also discussed briefly with the Meta if they were wanting to host the spring meeting, then we were discussing possibly have it earlier than this. June, July is kind of very full of conferences, and also depending on where Meta want to do it, one option could have been Las Vegas, then that would be extremely hot. So a spring meeting, but that would most likely also affect a little bit I would say the online meeting, because if we go for an early spring meeting, then maybe we should put the next meeting slightly earlier, maybe November or something like that. Okay, but yeah, maybe we don't. I will let's set up a call after possibly end of August, beginning of September, when people are back, and we can take a decision. And I will try to investigate a little bit options during the meantime. So with that, let's close this admin session and then
So
move on to the program.
Close, I still wanted to discuss the issue of, this, human factors group, because I know.
Okay.
There was like, it was not in favor of expanding probably the scope of the current human factors support group, that's, maybe there is like enough of more land to make like a separate one. I don't know, it's also the point of view.
Well, this is a question I asked, so maybe we can discuss how we do it, otherwise we can discuss.
Yeah, okay,
My question.
But we will not, I mean, if Patrick raised the issue about it and he's not here, it might be hard to do.
Yeah.
For me, I think if I got the idea, I don't think the new group prevents having, let's say, the old scope as well, but,
well, we could have like, the old group just working with IEEE.
Yeah.
Presentations.
If that name is somehow devoted to that, then you can always come up with a new name for the new group, but still I think it's kind of good to see how it distinguishes against IMG and ADHD. So I think where in that landscape would it drive its questions?
IMG is not relevant because it's just, immersive, and I thought about things that are not only limited to immersive technologies.
Yeah, I mean, that's fine. I'm not saying that it wouldn't be relevant. I just think one need to be, have distinguished it. I mean, set the goals so that's clear that this, and also with the name, probably.
Okay, the name is probably the least important thing now, but the scope, that I had in mind was like, the group that is just dealing with the behavior of the subject, the behavior of the user. It is partly covered by IMG, also partly covered by ADHD, but there are also like different topics there. And I thought, like, okay, maybe it would be a nice, maybe it would be nice to have something that is just, gathering only those people or only those presentations or only this kind of research that is not really looking at the service itself, but the human behavior.
Right. Yeah. Okay.
But I don't know if there are more people interested in it. No, I had my two peers didn't have presentations here, and for sure they will have some more. But of course, we need more people.
But then that just you to, or maybe together with Maria to make a proposal, and we can bring it up on the board meeting we will schedule. So we can take
we can talk.
And then maybe before the meeting we can circulate the proposal. Okay. Very good. Let's move on with the program. We would have a norm session with a presentation. Is there anyone, session leading the norm session? Okay, hearing none, we will have the presentation 46. Let's see what that is. It's Philip Poros.
Yeah, so maybe.
Hello, I will start sharing my screen.
Okay, yeah, please.
I hope you see it.
Yeah, we can see it. Yeah, please go ahead.
Hello, my name is Filip Korus. I am a bachelor student from AGH University of Science and Technology from Krakow, Poland. Me and our team from both AGH University and TV Hive company prepared presentation about detecting hard to compress video sequences based on objective quality metrics. As all we know, today there is a very huge demand for delivering IP video data. According to Cisco, there was a threefold increase in IP traffic over 5 years. In 2022, 82% of all IP traffic consisted of video traffic. An average internet user has almost tripled the amount of generated data over those 5 years, which again shows growing demand for delivering data. Platforms such as Netflix, TikTok, YouTube, and Twitch have changed the way we consume video materials. They provide access to a significant amount of content. A new category of content that significantly increases its share in IP traffic is streaming gameplay and esports events. During such events, professional gamers compete with each other, and their skills and determination attract attention around the world. Large esports events are as important as traditional sports events, gathering fans both during live broadcasts and those who watch retransmissions. However, despite the enormous popularity and demand for esports video content, technical challenge of broadcasting it live still remains. Video game content is difficult to compress, which can lead to loss of quality or delays during streaming. Even advanced compression codecs such as H.265 and H.264 in some cases do not process these materials well enough to achieve high quality. Compressing gameplay video sometimes is a huge challenge. This is because games are usually rich in details and there is a lot of motion because of in-game camera movement. First-person shooters like Counter-Strike are one of those games with detailed scenery and frequent and quick camera panning. To measure the amount of spatial details and motion in the video, three quality metrics were involved. First is spatial information, which measures amount of spatial details in the video. It is being calculated in 3 steps. Firstly, we apply Sobel filter on a frame of the video. Secondly, standard deviation over those pixels is determined, and the final SI value is the maximum over time of SI for every frame. And SI values over 200 means that video is very detailed. On the other hand, temporal information is defined very similar to SI, but it consists of the difference between 2 neighboring frames. Last but not least, criticality is the mean product of those 2 measures mentioned before. The experiment involves compressing all videos from our database with the H.265 codec at different bit rates, ranging from 100 kilobits per second to 21 megabits per second with 100 kilobits steps. Bit rates lower than 20 megabits per second are being used by TV Hive, a company that we cooperated with during the project. Bitrate of 21 megabits per second is being used only to check if there is any improvement over 20 megabits per second. Then VMAF levels are calculated for each bitrate variant of the compressed video. Same for SI, TI, and criticality. The plot on the right shows the VMAF value depending on used bitrate. As you can see, some videos from the database do not reach VMAF 90 at all. That means they are very hard to compress. But most of the videos are easy reaching the VMAF 90, even for low bit rates. On this plot, we can see levels of spatial information and temporal information for every video, divided into two groups that reach VMAF 90 and the other which do not. What is more, videos not reaching VMAF 90 have lower SI and TI thresholds than suggested by Margaret Pinson and showed 3 slides ago. This is because those SI and TI thresholds were defined before VMAF era. And those red crosses are the videos that do not reach VMAF 90, and their SI values are around 100, and they have TI values around 10. Taking into account the previously discussed behavior of metrics, depending on the content of the video, a machine learning binary classification model was created. It classifies the sequences based on the difficulty of coding. Spatial information, temporal information, and criticality and their mean values over the time are being used as input features to the model. Trained model achieves accuracy score of 92%, as you can see on the right figure. It has an excellent ROC curve. This chart shows which features are the most important to the model's predictions. As you can see, SI parameters and the SI mean over the video have the greatest impact on the classification, which means that the video containing a lot of spatial details is more likely to be classified as difficult to compress. This normalized confusion matrix shows actual accuracy of the model by showing the proportion of predictions for each class relative to the actual class. As you can see, model achieves accuracy score of 92%. To conclude, our model could be used to create balanced video database consisting of either hard and easy to compress videos. And in the future, this idea could be extended by creating a model that will tell us what part of the video is harder to compress. And based on those findings, we could temporarily change compression codec parameters to maintain the same quality. And that's all from me for today. Thank you for your attention. Do you have any questions?
I have one. How was the VMAF 90 threshold chosen? I mean, why 90?
Because in most papers, this value is considered as no loss of quality visible to the human.
You can add that Netflix, well, for example, somehow suggests this. I think there are many approaches to the lossless view.
Just
90, well,
so just one comment that if you consider the JMD, so the data set video set we computed 94 as a lossless transition from lossless to lossy, but it is very content dependent, of course. But on average, 6 VMAF or VMAF of 94 is considered as a transition. Yeah, that's also perfect, but just a comment here.
Thank you for the question.
Hi everyone. I would like to. I have also a question. Can you hear me, sir?
Yes.
Yeah,
yes.
Okay. Case Loic speaking. Thank you for the very nice presentation. I think it was in ICAPS 2019 or 2020, we presented the work where we were basically showing that VMAT might have some difficulties in predicting the quality of pictures, or I think in general of videos for which the SI index is quite low. So I was wondering whether in your analysis you consider the fact that the VMAF might not reach 90 due to its own inaccuracy. Like I am missing. I mean, it looks to me that your analysis is missing the fact that there might be itself some situation in which VMAF will struggle to predict the quality correctly. Did you take this aspect? I mean, the fact that the metric by itself is not totally accurate in account in your analysis?
No, we didn't take this into the account. You are correct that VMAF could not always be perfect metric.
Yeah, thank you. Yeah, I mean, thank you. The analysis also, again, in our case, we found that videos whose special, I think it was the special index, the SI was smaller than 40, where the quality of this video was hardly predictable with any full reference metric. And our hypothesis was that probably a full reference metric, are not able to capture the fact that the distortion is, very emphasized when there are few details on the video, on the scene. That was our hypothesis. Maybe it's something that you might want to integrate in the next development of your analysis. Thank you.
Yeah, that would be awesome.
One comment. Just one additional comment that, Philip, if you have time, it would be good to attend also the presentation 144 after the break. So I will be talking about the spatial temporal complexity metrics that might be useful for your method.
Okay, so I will watch it.
Okay, thank you.
Okay, if there are no more questions, then that's time to speak. So I think this is not normal in people, but I think we are ahead of schedule. So instead of so I think we just continue with the next presentation. So, and I guess that will be, isn't that you, Javi?
Well, I see one.
Maybe I make a mistake. No, it was 113.
Yes.
Yeah, it was.
Maybe Zhengzhong 2.
Yeah. See if you should already are online, otherwise we may need to take another presentation because they may have been.
Yeah.
Are they online? Let's see.
I couldn't find him online.
Okay, so maybe we wait with that until after the break, and we also have lined up Felix Gilmore.
Actually, this was mine, and I don't know why it was changed to Felix. So I can take and present if it's okay.
Okay, yeah, go ahead. Which number is it?
136. 136. It should be removed actually because it is the same as 144. So I will present.
Okay,
it is the same. I don't know why.
And 136
yes.
The same.
They same.
Okay, yes, it's good. So which title, which one should I delete from the list? Is it?
I think you can. You can delete the first one, 136.
Okay.
Good afternoon, everyone. I will be talking about the video complexity metrics. So the title of the talk that I selected is From VCA to Deep VCA because it is like a journey that we started 2 years ago. So we proposed first VCA and then eVCA and then Deep VCA. But I see that other activities are around. So yesterday I saw IVCA is also out from Chinese universities. So that's why I selected this title. But the motivation behind that, why we need the feature extraction for video, in particular for video coding, is that our motivation actually was for improving the live video streaming. So we wanted to extract some features that represent the spatial complexity and temporal complexity of videos. And in this way, we could respond some questions in video streaming pipeline, like where to import, if we have limited resources and we want to distribute our videos on different resources, so we wanted to know the complexity of the videos. Or if we wanted to select or optimize the bitrate ladder, we wanted to know also the complexity of video. The other question that we wanted to respond is that what encoding parameter we should select for encoding. And also very important to know that for video quality metrics, also we know that in most of them, spatial complexity and temporal complexity of videos play an important role. But traditionally, we know that SI and TI is used. So actually the motivation behind for SI and TI was that they wanted to cluster videos for subjective tests and select from each cluster some videos to do the subjective test to avoid having all the videos for subjective tests. I think most of you know that for spatial complexity, actually the Sobel filter is applied, as you can see here. And for the temporal complexity, simply the differences between two frames is calculated, and this is representative of the temporal complexity. But when it comes to the video coding, we realize that these metrics are not that much efficient. This was the motivation we started to think about this, that how we can improve this spatial complexity and temporal complexity metrics in a way that we can actually optimize our streaming pipeline. So imagine that we have a sequence of frames. So for each frame, we divide that frame into blocks. And for block number K, for example, we calculate the DCT coefficient, and then we calculate the energy function we called for this actually block using the weighted DCT values. And for each block, we calculate the energy of the blocks, and then by averaging over all the blocks, we calculate the spatial complexity. For temporal complexity, is quite simple. So considering two co-located blocks in two consecutive frames, we just calculate the SAT of the energy functions that we calculated for the spatial complexity. Here we can see that how does it work for spatial complexity and temporal complexity. Because videos are also based on the DCT, we saw that there is a higher correlation with our features compared to the SI and TI. So just as an example, I want to show one use case that we used actually this for OPT, or online per title encoding. We use this metrics to predict the optimal resolution for encoding to avoid having the fixed bitrate ladder. So for each bitrate that you can see here, we selected, instead of having the fixed set of the resolution, we selected the optimal resolution for live video streaming. And here we can see that when we encoded the same video at two different bitrates, at the same bitrate, two different resolutions, we can see that using this metrics, we could find the optimal actually resolution for streaming. And in this way, we could actually enhance the quality and the BD rate saving shows around 30% saving, just simply using this metric for finding the optimal resolution for encoding at each fixed bit rate. So we published this as an open source. So if you are interested, this is the QR code for VCA. It is quite fast. It can be easily used for live video streaming. We reached, I think, with 8 raised to 800 frame per second feature extraction for 4K videos. So if you need it for live streaming, so this is a good solution. But the problem with VCA was that the temporal complexity was more or less low, because it doesn't consider the motion compensation, right? So it is simply the differences between two collocated blocks. In particular for videos that we had lots of motions, so it didn't consider that, although the spatial complexity increased, but still we had problem with the temporal complexity. As you can see, it is just differences between energy of the blocks. Having this motivation, we introduced Enhanced Video Complexity Analyzer, or EVCA. So instead of calculating SAD between energy of the two collocated blocks, we first calculate SAD of the blocks, and then we average over the pixels of the block. And here, with this simple definition, we can see that our results is improved. So just features of EVCA is that it was implemented in Python. So for people that want to use it on GPU, this is more handy to use. It also has SITI implementation. The current implementation are quite slow, but you can use simply this EVCA also to calculate SITI features. Also, we added the VCA implementation here, EVCA. Again, you can run VCA also on GPUs. And of course, we have the EVCA implementation. In addition to DCT, we also added the wavelet, and we are planning to add more and more transforms here. Also, we have 8 bits, 10 bits, and still we are working to add more features here to enhance our software. In terms of the feature extraction, we see that we could reach around 1,500 frames per second for SITI for 1080p videos. The same, because SITI is simply a Sobel filter and VCA is simply calculating the DCT. So we didn't see big differences, although in the literature we saw that there is big difference. It came from the implementation, but when we use the same implementation, we see that the feature extraction speed is the same for SITI and VCA. So we had a bit lower feature extraction speed for EVCA because that we have more calculation to calculate the temporal information. But we could improve actually temporal information for actually EVCA compared to VCA and TI. We can see that more or less a meaningful improvement we have for temporal information. So this is also open source. We presented this in the last MMCs. If you want to have access, you can scan this QR code. But up to now, we learned that we have 3 important spatial temporal complexity features, so which were SITI, VCA, and EVCA, but all of them were unsupervised. Then we thought that how we can have supervised metrics for the video complexity analysis, right? We needed labels. The question was that what is the spatial complexity and temporal complexities definitions? How we can define this? So our response was simple. So we encoded all the videos, all the frames in intra mode, and the bitrate to encode each intra frame for us was the spatial complexity definition at a fixed QP. So if a frame is more complex, we need more bits to encode that frame, right? So for temporal complexity, we simply use the P frames bitrate that needed to encode that video as a representation for temporal complexity. So if 2 frames are very similar to each other, so we don't need that much bitrate, the temporal complexity is very low. But in the case that we have more motion, so of course this bitrate that is needed to encode that video is higher. Based on that, we proposed a deep learning method. So we actually had a backbone. We used simply, for example, EfficientNet to extract the spatial complexity, and this would be the representation of the spatial complexity. But we extracted from the spatial complexity features, some features, and we use the similarity between features to find the temporal complexity. Just to make it a bit easier, for example, here is the efficient network that we used it to predict the spatial complexity, but from the middle layers, we take some features and then similarity of this feature for the first frame and second frame is used as a definition of the temporal complexity. And here we can see that compared, for example, to SI that reached for a spatial complexity correlation of 72, E has spatial complexity correlation of 91 from VCA, but using different deep neural networks, we could reach even to 97% correlation with the spatial complexity or bitrate to encode intraframe. But this is more significant when we look at the temporal complexity. Here we can see that TI is only 43, H from VCA is only 46, but using our approach, we can reach to more than 80% correlation with the temporal complexity that, as I told, our definition of number of bitrates needed to encode the P frame of a video. So this was a huge improvement for temporal complexity. I will share the code very soon. I'm just cleaning the code. This is the actually QR code that you can have access, but hopefully very soon I will do this. So just to summarize that, we proposed 3 different softwares, open source softwares, VCA, eVCA, and DeepVCA. VCA was used mainly by CPU devices. It's a very optimized software. Then using eVCA, we enhance the temporal complexity, and with DeepVCA, we still could improve further the temporal complexity definition. As I told yesterday, I realized that we have a new version of VCA. They called it iVCA. I couldn't have a chance to read it, but this is also a new software for the extension of the VCA. But in addition to this, we had a motion search also from Meta. Unfortunately, Cosmin is not here now, but they also proposed one spatial temporal complexity metric, which is called motion search. This is also very interesting, and I will try to having all of them in eVCA later on. But having this motivation that the community is working on this metrics, so we talked actually with Ioannis to have a special to have a grand challenge in ICIP. So we organized a grand challenge in ICIP. So we called it GCVC, or Grand Challenge on Video Complexity Metrics. So the organizers were Ioannis from Meta, it was myself, Ali, Anil from Trinity, and also Christian, and this was sponsored by Meta actually. Then we defined some rules for this grand challenge. The rule was that finding the bitrate when we encode a video with AVC at CRF of 26. So this was our rule, but we wanted to have metrics that actually are quite fast and accurate to predicting this bitrate. So we also asked participants to use the Inter4K dataset, which includes 1,000 video segments. We got significantly a good number of the contributions. In a very short time, we got 18 contributions. Actually, they used different approaches. One of them was deep learning approaches. We had BitStream-based approaches that they used the BitStream information of the input video to predict the complexity of the video. Some of the approaches, 3 or 4, use VCA to extract the features and predict the complexity of video. One used motion search. I think it was from Germany. Lots of the methods use fast transcoding. So when you have a 4K video, 60 frames per second, they downscale the video, downsample the video, then they encode the video very fast in ultra fast preset and use this as a feature to predict the complexity of video. We also had other approaches that I don't recall what they used, but we had also 2 or 3 more contributions that used other features to predict the complexity of the video. The plan is that we want to organize next year as well in ICIP, so I would appreciate if you also could contribute to the next year. We will not have next year that much in a short notice, so we plan to have a better version of the grand challenge for next year, but we also want to add other encoding parameters, for example, varying the spatial complexity, temporal complexity, and etc. So thank you very much. I forgot to put a thank you slide, but thank you.
Questions? Enrico?
Yeah, I mean, I understand that what you do is basically to save on processing time to do actual encoding at multiple bit rates when you do live streaming. And do you have a figure that you can share with us on how much you can gain from using this kind of approach compared to, I don't know, some baselines?
Yes, sir.
Baseline approaches.
Just one example here, we showed that just using these features to predict the optimal spatial resolution, we gain around 20% to 30% bitrate saving. But we tried also on other encoding parameters. For example, we also tried to find the optimal frame rate for encoding, optimal CRF for encoding, and those many encoding parameters, we could optimize over them. We usually get between 10 to 30% bitrate saving when we could, for live streaming, predict the optimal encoding parameter.
Do you consider also down scaling tempo resolution, kind of like lowering the frame rate, not only the resolution?
Yes, I mean, this was actually, yes, you meant for the optimal frame rate selection,
Yes,
right?
yes.
Yeah, actually, in another paper, we proposed to find the optimal frame rate for a fixed bit rate. So it was a very similar, actually, bit rate saving. In that paper, for that data set, I remember when we just only using the spatial complexity for optimizing, we got around 15% bitrate saving. By adding also selecting the optimal frame rate on top of the optimal resolution, we got 30% bitrate saving. So, but the problem there that we don't have very good video quality metric that captures the frame rate changes. So this is the problem that we have. What we do is that we duplicate the frame and then we calculate frame by frame VMAP, which is not appropriate way, right? So I believe that we can actually get more bitrate saving if we could have a better metric than what we do right now. Because it's imagine for the event frames, we have lots of drop in the quality, which is not the case when we are watching the 30 frame per second video compared to 60 frame per second. This is still a research question for us there. I know that there are some activities, but still, I think we need to find a better metric to capture this frame rate changes.
One more question. Do you have an idea of how this metric would perform if you have some more extreme sequences, like sequences with very low motion, or sequences with extreme motion, things like that? I mean, these sequences are more like all really, besides text takeoff, I think they are all pretty conventional with motion.
This is from our very old paper, but yes, we also tried on 1,000 videos, and on overall we had a very good performance. But it's still, as I mentioned, our main problem is the quality metrics here to see that we rely on VMAP, for example, after upscaling. I'm not sure it is really reliable or not. PSNR is reliable or not. So, but we use VMAP and PSNR for our experiments, but I hope that we will have better metrics to represent this kinds of activity.
Okay, thank you.
Thank you.
Also the presentation 145 of Pierre Le Breton, maybe he is also.
No, I'm here. I can do the presentation.
Okay, excellent. Okay, please go ahead.
You should be able to see the slides.
We see.
Okay, so I can start. So good afternoon, everyone. So I'm Pierre Le Breton. So today I'm going to present, this work that we have done together with our colleagues from YouTube. So Nir Bilbek, Yiling Wang, and Balu Absumali. So what I'm going to present is this data set. So this work is actually something that is going to be published at ICIP 2024. So this is an early version of this work. So this is within the track of the data set of ICIP. So at first, a bit of motivation. So this addresses the question of user-generated content, so UGC video. So as you know, this is a major application of the internet. So it represents a large part of the traffic. So anything that can be saved, in terms of bits, while streaming a UGC video, can actually have a large impact on operational cost and ecological impact. So the quality of UGC videos need to be understood. So as we all know, there is a lot of quality prediction models that are quite well performing, such as the VMAF and also the IQT P12X series. But this type of model assume that the reference is of perfect quality. So we need to have so in order to be able to evaluate the quality of UGC video, we cannot always assume that this is the case, that the reference is of perfect quality. So we need to have no reference quality evaluation models. So there is models like this, for example, UVQ or Videval that have been published. But then there was a different question that we were wondering. So on what type of data these models were trained, and how the impact of the training data will actually affect on the performance of the quality prediction models. So there is different existing UGC data set that exist, and then we are wondering how does this data set relate to each other. And then there was also the question of how UGC quality prediction model can also handle both the question of ingest quality, so the quality that they will receive on the server side, and then how they are also able to evaluate the quality of transcoded video. So when they aim to stream the videos back to the content. So in terms of state of the art, there is a lot of different UGC video quality dataset that have been published. So here you have a list of these different datasets. So you can see that they actually include they have different properties. So they can have different resolution, different frame rate, and different quantity of content. They were evaluated on different scales. So it could be a quality, but also some start also to look into aesthetic and so on. So we thought that this was actually quite interesting because all these data set actually, every time an author try to make a new data set, he aimed to have a large variety of content and a large variety of type of impairments. But then there was the question of the alignment between all these different data sets, because once you start training your UGC quality evaluation model, so you may, for example, start on YouTube UGC, but then the question of how this quality prediction will actually be valid for another data set. So there was a question of alignment between all the data set that is a no. And then we were also thinking about other things than quality. For example, how about acceptability of those different videos? So these were the different things that we wanted to address. So we conducted a subjective experiment with the goal of understanding the relationship between existing open UGC dataset. So the goal was also like to study like the prediction accuracy of existing UGC quality prediction model, both for ingest and transcoding quality condition. And then we also wanted to study the relationship also between acceptability and quality. So we conducted a crowdsourcing experiment, so which was based on the Prolific. So we had 1,080 videos, so 326 ingest video that were then transcoded at different quality levels. And all these videos were evaluated both in terms of acceptability and quality. So we had at least 32 rating per PVS, and also at least and each participant during the crowdsourcing study rated 40 videos. So it took about 10 minutes for them to complete the test. So the first question was, so how can I actually do like this, build this data set that we wanted to evaluate? So the first thing that we did was like to study all the different existing UGC data set. And there you have like the distribution of the subjective rating from provided by the author of this existing data set. So what we could see here was, for example, that different data set may have like a different distribution of quality rating, which is quite interesting because it will have actually an impact on the prediction model that will be trained on those data. So as you know, for example, the YouTube UGC dataset, you can see that most of the videos actually have a rating higher than 3 on the most scale. So, which is also a reason why if you applied UVQ that was actually trained on those data, frequently tend to have a prediction that is at least 3 because the training data was containing mostly videos that are higher quality than 3. So this is why we thought that it's actually quite important also to think about like the distribution of the quality rating of the training data set that is used actually to train UGC quality prediction model. So what we did to build our data set, so we actually collected PVSs from videos from each of these different data sets. So we aim to have like a spread of the quality. So you can see on the scatter plot below that we took among all these data sets. So on 6 of these data sets, we selected videos that will be considered as ingest quality, so directly taken from this data set. And then we aim to cover the quality scale. So then we wanted to add a different coding condition. So for this, we encoded the videos using VP9. So the general idea of this encoding procedure was like we took one of the video that we selected before from an existing UGC dataset that we encoded at various CRF. Then we estimated the quality using VMAF. We actually know the quality of the ingest based on the subjective rating that is provided with the dataset. And then we actually evaluate like the DMOS, so the distortion that we add by transcoding the video using VMAF. Based on this, so we can have like an estimation of what will be like the quality of the transcoded video, and then we build our dataset in such manner so to have different coding conditions that spread the quality scale. So then the goal here was to have a dataset that is more uniform in terms of quality. So here you can see like on the scatter plot for each SRC we have like a different range of quality values. And also we wanted to have different ingest quality values, so as we selected before, so we can study separately, so ingest quality and then transcoding at different quality levels. So the experimental result, so we did the screening of the participants, so using Surreal, so as based in ITUT recommendation P910. So what we will go here, I will present actually the result of the comparison between our collected crowdsourced experiment with the subjective rating that was actually obtained from the author of the dataset. So there we can see like a different dataset may have different alignment. So for example, you can see like for example the YouTube UGC in the original rating from the author, then they tend to have like a higher quality than what we actually measured in our crowdsourcing experiment. In some cases, for example, in the Netflix dataset, we saw that it was actually quite aligned. What was actually quite interesting for us was actually the live VQC dataset. So we actually selected some of the video from this dataset in order to cover the quality range from the author. But when we actually evaluated the video in our crowdsourcing experiment, we saw that actually most of the video were of high quality as rated by the observers. So we saw actually that is more related to an issue with the context of the evaluation, because in the case of the live VQC, you also many have artifacts related to captures. For example, you can have like autofocus issues and like cameras that is trying to make the focus on the subject and then lost focus and then redo focus. So in a data set where most of these artifacts are such are type like this, so where you're more related to capture, if you put it in a context of compression related experiment, so like we had here with many coding condition, then all these type of autofocus issue become a completely different type of artifact, and actually led to different type of ratings. So once we established this dataset, we also wanted to look at the quality prediction of state-of-the-art models. So we saw that actually state-of-the-art models are actually performing quite well on our data. So we have like two versions of UVQ. So I wouldn't go too much into detail, but UVQ have like a different branch and different versions that have a different focus. So you have like these two different versions of UVQ. You have Dover, which is also like can have like different focus, more towards aesthetic, more towards technical quality and aggregation based on that. And then you also have like other models such as simple VQA and so on. So there we saw actually that this model were actually performing quite well. Then what we were wondering was also like the difference between this state-of-the-art model. If you compare actually the performance of, because on our data set and compared to the score obtained from the original author. Because as you saw before, so we actually took that were existing from existing UGC dataset. So we already have the score from the original author, and then we have also the score that we evaluated in our crowdsourcing experiment. So that we saw before, like with the alignment of the different dataset. And then when we actually look at the performance of UGC quality prediction model, so when you compare actually the performance of this model on the specific PVSs that were evaluated twice, I mean, by the author and of the UGC dataset and by us. And then we saw that if you look at dataset that were actually evaluated more in context of UGC quality evaluation, we saw that the model were actually performing quite similarly. I mean, between the performance that you had, for example, on the YouTube UGC dataset and the score that we actually collected. But we saw like things, for example, like professionally generated content, like the Netflix dataset. Then we can actually see that actually being able to align the quality score from the Netflix dataset to the UGC dataset actually allowed to have a much higher performance for the existing UGC dataset. So you can see, like for example, faster VQA got almost a 0.8 SRCC gain between the initial prediction accuracy that we had from the data, I mean, from the Netflix public data, and what we actually evaluated in our data set. So it was also quite interesting for the live VQC. So if you look also at the PVSs that we actually evaluated, so state-of-the-art model actually was not able to predict the quality of the PVSs if we used actually the rating of the author. But we saw that when we actually put this video in a context of coding-related experiment, then actually state-of-the-art UGC quality prediction model were actually performing much better and were actually performing very well on this live VQC dataset. So the conclusion there, so we saw that existing UGC datasets are not aligned. So we have different datasets that were also evaluated in different contexts. So as we saw, for example, with the live VQCs, that actually leads to differences in terms of ratings and also like impact actually the perceived prediction accuracy of UGC video quality estimation models. So with our dataset, we also aim to align existing UGC dataset in order to be able to have a more robust training of UGC model, emerging dataset, for example, like the YouTube UGC dataset with the Youku V1K dataset, and also like put also in perspective with Netflix public dataset. So I think it's actually quite well because it's quite interesting because it actually allows to understand the relationship between the quality score of these different UGC dataset and also like be able to train UGC model in a more consistent manner since actually all the different data are aligned together. So the dataset will also like be published on Zenodo. So at this time, I'm still like preparing some final things for the publication of the dataset, but you will find the dataset available at this DOI. And that's all. Thank you. Do you have any questions on this?
Yes.
Yeah, I have a question on your chart that has all the results. I think there were 4 tables, this one.
Yeah.
So which one is the best model at the end of the day for prediction? They seem to be changing depending on the data set. So I see UVQ is good on the first, on the left table. What's your recommendation?
Yeah, actually, so what I saw is if you actually merge all the different datasets and put them together, so in our final dataset, actually the best performing one was like a faster VQA and a faster VQA. And Dover was actually also on, if you look at the technical feature, because our dataset was mostly focusing on compression and not really too much about aesthetic quality. So Dover was also quite well, but faster VQA and fast VQA were actually performing the best. Then if you look at on a per dataset basis, you have some differences, but you can see again that fast and faster VQA still tend to be among the best one. The live VQC, we don't have too many PVSs in the dataset, so but you can still see like in the retrain version that we had was faster, and fast VQA was also performing quite well. So at this stage, I would say these two, fast VQA and faster VQA, was like the highest performing. But then depending on the dataset, yeah, for example, if you look at specifically the YouTube UGC dataset, then the UVQ model, which was actually mostly trained on the YouTube UGC data, then was actually the best performing. But in general, I would turn to the fast and faster VQA.
Thank you. Very good work.
Johannes? Okay, in that case, let's send the speaker.
Thank you.
The next presentation is also Norm, but maybe still by Shelton too. Are you online? Okay, so maybe we have to wait with that until after the break. We also have two presentations in EETG, but they may not be online either. Yeah. Sorry?
One of them is mine.
Ah, okay. Do you mind doing? Is that what? Which one is that? 142 or
I think 142 is my number.
Okay. Yeah, but let's go. Yeah. Okay.
Okay. So this is my presentation on updates for testing activities in NTech V2A. This is my third WCAG meeting. I'm very happy to be here, and my intention is to strengthen the connection between WCAG and what is done in NTech in terms of quality assessment. So part of this is just reporting what we have as activities as plans, and some parts is a little bit on some analysis that we did and some activities that might be of interest. So first is updates on testing activities with JPEG, with JVET. We have some verification tests and then quality testing going on. It's always something that comes like at the end of a test standardization activity where we want to demonstrate how well let's say the goals of standardization effort have been achieved. And the second bullet that I have here is maybe a bit more interesting. That's the status of the current development towards a potential new standard out of that group. And we did a subjective assessment on that topic. So we'll summarize that a bit. Then we have two calls for proposals that are in the queue. One is on AI PCC, so neural network-based point cloud compression. The other one is on lens reporting. We had something on that earlier on. Then we are building up a database which is for compressed video for study of quality metrics, which I think is quite important for the standardization task because we want to learn how the metrics work with content that has been compressed by neural networks. And we know that that the metrics may have difficulties with this, so we want to characterize those and learn what we could do better. We have an activity on interactive testing for visual volumetric media, and then I want to briefly summarize a study that I did together with Joel on these remote expert viewing tests that we did during the Corona times. And so we did a study on what has been done there, and so I just want to capture that. But the first two, I think I can be very quick because I reported on that in the December meeting, and there's not so much development since then. It's quite difficult to get a lot of work done there, and that would be needed. So we found in the October meeting that we might have an issue with the test model for PVC to code multi-layer video in a visually nice way. And the effect is that if you do subjective evaluation and you compare like single layer coding with multi-layer, then suddenly strange things happen. And that's a bit unfortunate. So we need to first improve the software before we can continue conduct that. But the main goal would be that we have single layer coding. So we have a full resolution video that is coded. And we would have let's say half resolution video that's coded and upscaled, and the upscaling would be done with the normative upscaling filters that are provided with VVC. So that's kind of the easiest thing that you could do. And the third one then would be two-layer coding, and ideally we'd have a curve where the single layer would be best quality, the multi-layer thing would be below that, and then the upscale base layer would be below this one again. but this is currently not true. So there's a technical issue that we have to solve. And the other one is on film grain, which is not a verification test because it's not a normative thing in the context of BBC, where we're collecting the data. So this is something that may actually take place now in the last quarter of 24, and then we might be able to report on that. So the first thing is there that we use the film grain, we evaluate the capability of the film grain to hide compression artifacts, or enable coding of a somewhat transparent quality at a low bit rate. These two things are close. And then the maybe the more interesting one, at least from the perspective of the standardization group, this is the second performance evaluation for of this enhanced compression model, so the ECM, which is new tools beyond BBC against the verification test, the test model for BBC itself. The report is going to be submitted soon. It will be document JVET AH 2029. Those JVET documents are all public, so there's you can just download them from the JVET site. If you search for JVET experts, you will find that. And so the comparison was the VTM, which is the anchor, and then the ECM, which is the test model at stage 12, and then the second version of that, which had no template matching tools enabled. So the idea was template matching tools are super expensive in terms of computational cost, and the idea was to see how much effect those have. The test was planned to be on site, so it was run during the JVET meeting, so it should be very fast. And we decided to have 3 UHD sequences and 3 HD sequences, and UHD would be done in random access streaming type of configuration, and the HD ones would be low delay, so that would relate to a conversational application. And then we had it somewhat downsampling, so you see here the tables may be hard to read, but so for the HD we would have the full variants with 2 sequences and only the VTM, the ECM for the third sequence, and for HD we did the other way around just to reduce the number of test points. That was what we did, and all were done with rate matching so that we would have a quality rate alignment. So these plots, I don't want to go into details, are just the plots for in terms of PSNR for the Luma, and you see that there's typically a shift, so a gain for the ECM, something like 20 to 24%. So there's actually also the range that we have on the test set, something like up to 25% for random access is what we observed there. And for the HD sequences, it's less because flow delay is much more challenging. Right? So these numbers are in this ballpark. And what you also see is that these 2 versions of the ECM, so the full version and the one without template matching tools, are pretty much close, right? You don't see much difference here in the curves. Now, if we, first quickly on the logistics, actually we had quite nice conditions. We were provided with 4 65-inch OLED screens that we were running from a viewing PC by a splitter, and so we actually were able to do the 4K raw 4K 60 Hz 10 bits play out fully to these screens. That was very nice. And we did the setup such that we would have 3 viewers per screen at 1.5 H distance, just to be fast, because we needed to get these things going through. And the HD stuff was then centered in the UHD screen, so that we would not need to change the position of the seats, but just continue with the same setting. We used the DCR method. I took that advice that you gave at the last meeting, that we should not have this multi-dimensional scale, so we don't use that anymore. We did it this way. And I have some examples just to show you. Basic messages that the subjective numbers roughly are in line with what we have objectively, which is something that we actually did not have before, typically. Because typically we would have more subjective gain than we would have objective gain. And one assumption is that this is due to the fact that we don't have a paradigm shift in what is done. It's basically all very evolutionary. There are no significant new tools. It's just variations or more elaborate variations of tools that would be there otherwise as well. So transform sizes didn't change so much. We already had code-aside motion vector derivation, all these kind of things. So it's not so much of difference. There's not like one tool giving you 10%. That was something that was different in previous times. And what's remarkable, that's why I have this curve, is that it turned out that there's a subjective problem with the template matching tools. That was something that we were not aware of before, because the PSNR numbers actually told us it should be pretty close, right? So if you look at the beach mountain sequence, you would have something like 1% of Biontega delta loss over the whole range. Now, if you look at these curves here, the light blue is the one without template matching, and this was very different. Okay, so this is one aspect. So this was quite interesting and a good finding, and also a finding which is alarming because the metrics didn't tell us. Right? That's something that was important. And so what was also done, there were actually 2 small experiments, so it was not so many people, so we have to take these numbers with a little bit of care, but there were 2 laboratory tests done at the same time in Rome, and that partially overlap with the results, partially have some like here for these. There was, I think there was a group of four people just watching the sequence, and they actually consistently rated the version without template matching better for all sequences, for all other cases, which was not the case in RAN at the meeting site. Okay, we have some more. So like Dragon POV, that one behaved a little bit more like expected, so slight benefit for the matching tools, and a little bit more gain maybe for in terms of Biontega deltas, but not so much. Right? So this was it. That's for this part, and actually out of these numbers, it may look like there could be a potential start of a standardization activity at late 25. Right? And if that would get more concrete, I actually might want to reach out to people in this room to help conducting subjective tests, because in the last round, when it started with VVC, I think there were 35 proposals that were submitted, and so typically that would be something like, let's say, 8 to 10 or 12 sequences, 4 rate points each, maybe in 2 configurations or 3 configurations, times 25, 35. So that would be the number of test points that we would have. And probably this might be a huge testing activity that we would do. So a lot of coordination needed with lots of participating labs. And yeah, so this is something, if these things go toward that direction, I probably will reach out. And so would like to call for laboratories who would volunteer participating in the activity. I think similar things happened before. That was coordinated by Vittorio with multiple labs. We will need to do something like that, also to distribute the workload among labs.
Yeah, was for the 3D.
Also, yeah. So we have that over and over again. Right?
All right.
It's always when you and this is the major one. So this is probably the biggest test that we would do in the next or in the last 10 years. Something like that.
Okay. Yeah.
So I'm talking about VVC succession, not this one. The AI PCC is much smaller. It's something like 4 or 5 proposals being evaluated. So that's something that you can handle with 2 labs participating or so, but not the other one is a totally different scale. So that's something that may happen. This one is a follow-up report that I want to give you. I showed this slide, almost exactly that slide, I think last time again. This was an evaluation that we also did by an expert viewing at the meeting site, where we had these point clouds once, and they were evaluated once with texture and once without texture. And what we did in the meantime, and maybe I should skip this part, we did an analysis on some objective metrics on this data, just to see how that worked out. And we did this analysis using this tool provided by Lukáš, on the accuracy of faulty metrics, just analyzing how to work, just briefly how this would be to be read. You see the numbers down here in the below the graph. That would be the numbers that are in this table, and then whatever says IB in front would be image based. So this is something that was computed from the rendered video, and then computing these numbers. And the last three are based on the point cloud, right? And so the D1, D2 metrics are purely geometry-based metrics, right? And then the PSNR in this case would be the one that also considers the texture. And the core message here is, I mean, you see that the capability of differentiating very different and very similar qualities by these metrics is somewhat similar for all, right? This is what you basically can read from those, and there's no significantly better or worse metric if you go for this regard. Now, if you only look at the ones which are clearly distinguishable, and then you look at those metrics, then there's a very significant difference. So the left ones are the ones where the texture is included, and you see that the last metric is the PSNR on the that was computed on the point cloud, and that one's the best one in this exercise, and that's something that was really surprising. While you see at the same time that the D1, D2 metrics, and then now looking at maybe the geometry only, for the geometry only case, the geometry metrics are actually the worst ones compared to if people just look at the geometry, the rendered geometry, and then just confirming this. And we thought that the reason might be that the D1, D2 metrics ignore holes in the meshes. And this is something which is really important, because for the subjective viewer, the holes are killing everything. So it's super bad, and the metric simply doesn't look at those. Right? So if there's a big hole and everything else would be fine, then these D1, D2 metrics would report super high numbers, very good numbers. And this is not in line with what should happen. So I think if these metrics should be used for the purpose, maybe there would need to be an update so that holes could also be regarded. This is, I think, the main takeaway that we had from this exercise, that there's really something like that hidden below. Right? Okay, then this is just to announce that there's a call for proposals for length-wide video coding. I saw some contributions on this also on databases. The content that's currently considered for the CFP, it's not so much content that's available, and maybe there could also be a connect. I'm reaching already out to the guys from MPEG to maybe make contacts and just see if they could use something from what has been presented here. But so far considered in terms of the evaluation. So remember what the goal would be for the subjective evaluation would be the decision, which would be, if you have a number of proponents, which would be the best candidate for starting a standardization activity for the stuff. So we need to have something which is reliable, and it's also acceptable for the proponents. So we cannot be ultra fancy, and I would not like to do anything with it, for example, with candidate metrics in this regard, because you never know how those would react if they get something which is new. And we typically, in the context that we are doing these evaluations, we typically have compression artifacts which have not been seen before, just because it's new compression tools that are evaluated. So currently the concept would be that we simply render to the video at HD resolution, or well, the number of lines of HD, and then it depends on the picture format that they provide, the content provides, and then we would just do a GCR test in the laboratory for the evaluation. That's basically what we are currently planning. I mean, technology-wise, what they're considering is something like you would have a set of tools that adapt the signal so that you could have a regular BBC encoder, decoder in the middle, and then you decode. This is something that's also done in other contexts like MIV or so, where you would have something that sometimes they call it the inner codec, and the inner codec would just be the regular compression scheme where also tips are available, and so that would make it very easy. And then you pack everything else around that thing without changing the core. Okay, then on our data sets for the study of quality metrics, there we now have two MN-based codecs that have been submitted for being in this test set. So we have the VTM and VVENG. Those two are implementations for VVC. We have the HM, so test model again, and X265, which would be two representations of what we use for HEVC. And then we have mask CRT and NVC. Those are two neural network-based codecs, which are now used for evaluation. We have a bunch of sequences. Currently, we only focus on HD sequences. So the current codecs here can only do HD compression. It's quite challenging for neural network-based codecs to handle UHD just because of the size. And also there's not so much training yet available, so that we don't have a proposal yet for UHD. So we make a phase one, which would only be HD. Well, we have eight sequences, and we evaluate 4 breakpoints, which would be in the range of qualities, which is somewhat good for the purpose. So like covering the easy to watch visual quality range. And what's the status of work? So we have 192 test points that are evaluated. We have 4 labs that participate. That's Aachen, that's myself, VITech, HHI from Berlin, and USDC from China. And so we did a pre-experiment with these guys because well, Vittorio and myself did some tests before, the others did not so much. We made an exercise with them, and which actually worked out well. And then we designed common instructions for the participants, common instructions how the laboratories should be set up. We designed the test sessions I did that with Vittorio, and then we basically gave that to the laboratories, and this is now just going on now. So I completed my tests last week, and the idea is that around the MPEC meeting, the others would also complete theirs, and then we will do some analysis. So maybe in December, I could report back what we would have there to see what are the results. Okay, so that's going on. We have another activity which was proposed to have more interactive testing of immersive video, right? So what we typically do in MPEC, very conservatively, we just have a rendered video by a view path, which, if it's a call for proposals, would not be known to by the proponents. And then we run a conventional test on this, and this is taken as results. And so the idea would be that we have something that we can also run more interactively, which would reflect more the application that's foreseen for this type of data. So there's an ad hoc group working on the topic. We had a ad hoc group meeting last week, and it seems like the results that they were able to produce recently are actually exactly matching what we did with the conventional session, which can be a good and a bad message. I think the good message would be we can just do it with a conventional thing, because it's just providing the same amount of information. But we want to see, because it's, to some extent, I think it would be more natural to test immersive by immersive methods. Actually, if there are updates, I didn't see so much activity on the ITU side in this regard recently, but maybe I missed it. I would be happy to get some updates if there are standardization activities going on for getting the immersive approach somewhat stabilized so that we could use that. That would be very, very interesting to do. And if this activity turns out to be something where we can report on, I probably will report back also from this side. But it's something that would be of great interest for this work. Okay, and then the final thing that I wanted to report, I think it's the final one, is on the remote expert viewing test. Joel and I did a paper on this, which just has recently been released finally. And what we did there, so we had, I don't know, something like 8 meetings long or so. We had a lot of remote expert viewing tests that we did on various topics, like comparing loop filters, comparing network-based tools and conventional tools, performance assessments, deep blocking filters, all different types of things that were evaluated with this method. And so we had a lot of REV data, so remote expert viewing data, and we then made a sub-selection of that for a formal laboratory test that we did with PCR. And then we did this, and then we ran that on those sequences. We also ran 13 objective metrics, a bunch of just conventional ones, a bunch of learning-based ones, and did a thorough analysis on how these work. And the main takeaway messages would be that the remote expert viewing actually worked. I mean, this is something that we did. Well, we provided MP4 files to the participants, to the experts that were distributed in the world. We did, and they used VLC for playing. So very, very simple everything. And still, it was found to be reliable. So the results were okay for what we got there. And it seems also that they are actually quite okay in terms of discriminating also small things, which may be more difficult if you have naive viewers. Right? Of course, you may always have a bias by people who are on the test. If you talk to loop filter experts, then they will rate loop filter artifacts differently than naive viewers, these kind of things. And what came out, which is also maybe a bit surprising, so PSNR, SSAM, and MSSAM were the best ones for on the conventional metrics. So PSNR was not that bad. Right? And for the best ones for learning-based metrics, that was VMAP and APPT. Okay, yes. And that's basically what I wanted to report. So we move on, and I'm happy to interact and get also advice from your side if you feel that we should do things differently or enhance it. Thank you very much. Thank you.
Any questions? No. Thank you, Matthias, for the very good overview about the data set that you have mentioned. How can we access or how can we use it? I mean, for people outside of that.
Yeah, this is a point. So currently, to make things easy, we started doing that inside of MPEG. So for people in MPEG, they can just ask and then they get the access. But it's not fully public. That's also because there are some sequences inside which have a license for use in standardization. So we actually, my intention would be that we try to make that public at some point. Yeah, I know. But it's a difficult thing. We have to sort it out. But it's so one thought that I had was maybe, I mean, we want to do this in a kind of a incremental fashion. So because the neural network-based codecs are developing so fast, I guess the data that we collect now on those codecs will be outdated for codecs that come this year or next year. So probably we will repeat that. And if the mechanism is established, then we might easily go and say we open it in some way. Or partially, or maybe we can also find a way to somehow get more access to for the data. But it's not the best option. It was the fastest option that we went for.
So about the scale that you showed, I think it was slide 6, and that's 11 points, right?
Yes.
Why so many points and not sticking to the usual 5?
In the MPEG community, people have adapted to the 11-base scale quite a bit.
Yeah,
but I think it's an historical reason that one proponent of the 11-point scale engaged in MPEG test.
Yeah. And so the people are used
to it.
It has
name and surname.
Yeah, so I feel fine. I feel fine with using that scale. I understand that many people prefer to have the 5 points because it's easier, right? What I like about this one is that you would have 1 point specifically saying it's imperceptible for the VCR test. If you have the 5-point scale, then it's not so easy because you would waste a big number for that 1 point. But it's I have students. I mean, I typically when I run tests in Aachen, then I would call for students at Open University with people, let's say, between 18 and 26 or so. And I heard quite many times that they wanted to have more than this 11 points. Right, it's I understand that many people there are camps on this topic. I feel I don't know. Yeah, it's maybe the 11 grades are okay. Or do we have a strong concern about it?
Discussions.
I know. I was thinking how much you gain or maybe how much you lose if you use a Falcon scale.
I think nothing actually.
Yeah, I mean, this would be the question. So let's say I do it with 20 people. Is the 11th grades or is the 5th grade as good as the 11th?
I think.
Many days the confidence interval is larger than it depends on the.
But I mean, I would like to have small confidence intervals with numbers. I mean, the numbers are fine, right? But if the confidence intervals are smaller, then this would be a good reason.
I think it was something like 50 or maybe more years ago when NTT made this huge study comparing the scales, and the bottom line is actually it has no real significant influence on the results. So then we stayed with 5 because it is.
Yeah, but I mean, it's also okay to stay with 0 to 10 for this community.
But you can also argue that that's not an 11-point scale. I mean, then you have 7 labels. It's basically targeting people to go.
They should be more distinctive. Yeah. I mean, we have only names for these for a lower number of fonts. That's true.
Right.
Patrick wants to say something.
Alors, should I present the thing that I presented at PCS?
Yeah.
Yeah.
Do it again.
It's all about that. But Maya, the work, right? It depends on number of observers, availability of these observers, so time we get them on the benchmark, say, log them to do this type of thing. Yeah, it's all about that. Maybe I should present that.
It seems that we are very time efficient, so there could be time in the afternoon to present that.
But the thing that at least I have to acknowledge is good that you remove the other part of the scale. Because for the expert viewing the protocol, in addition to these 11 points, you have a second item that makes you select between 10 and 9, 8 and 7, related to the if you see some artifact somewhere or everywhere.
Yeah, we discussed that last time.
So this one has been removed. You don't use this anymore, right?
Yes.
And I think this is super well.
Yeah. It's fully okay.
And as long as we are experts, limited number of experts, and we can log them for a long time, I think it's very fine.
I mean, so my task is, if I do these things specifically at the meetings, I want the group to be convinced that what they get out is true, even if it's not what they expect. And so I need to do something which is, it should not be too artistic. So if I have too much statistical elegance in it, then people might start arguing, oh, it was not enough people, blah, blah, blah. So having something which is easy to understand, which people can accept, and this is also why the 0 to 10, they know this stuff. And it doesn't hurt, right? That's what we just learned, right? So that's the way. You could probably be a little bit faster maybe, but I think at the low numbers that we have, it's not so far from a good solution, right? And since I can do parallelism with the viewers as well, right? I mean, I had 12 experts watching it at the same time. Otherwise, this would not be possible at a meeting.
If you want to get that a bit, I think you can get probably better at some experimental effort without wasting the time of your expert, because it's extremely boring.
I think it's very educational.
Yeah, you say that, but you know, after the presentation at PCS, Jens came to me and said, "Oh, I have to admit this is my fault, this scale and everything." He said, "But I have to admit also, I don't like to do this figurative test. I'm not 3 hours to do this type of thing."
But it's not so long. I think for the experts, it was something like less than 2 hours.
Yeah.
Right? So they came, I informed them, I did
Less
the
than
same.
2 hours, yeah. Okay, okay, but I think it's already too long for Jens, but.
You must understand, so if I have this group, it's 300 experts in the room, right? And if I say, give me 5 and I do this experiment by some method, I have 5 people and they will always question, oh, this is a guy from this so-and-so camp, so there's a bias, right? If I have a sufficient group, then it's somewhat mixed, right? So having this kind of saying, well, if I pick a hand-selected set of 5 people, I can push the result in any direction I want.
Yeah.
Right, so to some extent, I also need to build trust by just saying I have a large group. It can be very mixed, and then they cannot attack me by saying I took the wrong expert.
Yeah. Yes, and I think it's important also that you have this type of activity as part of GF. But once again, to mitigate, it seems that when we compare experts versus naive, with simple scale, we get similar result at the end of the day when we just accumulate the number of naives. And in terms of cost, experimental effort, and so on, it's really, I think, kind of interesting to stick to SCR, HR, remotely, to do a lot of things. Nevertheless, when you have specific device, specific codec and everything, like probably this test, you cannot operate that remotely. Right? There's no way you can do it because you need a.
Actually, I believe that people, typically at home, people don't even see 10 bits.
So,
right?
yeah,
Because
exactly.
they probably have mixed up the setup and then they don't see it. You have to be super careful. And I'm not, this is SDR. If you would do HDR, it's even worse. Right?
So my take on that is that when you can do it remotely for technical reason, do it remotely with naives. And when you cannot do it this way. That's what I think.
I think I will do CFPs always in the I want to have full control. Yeah. If you have some proponent knowing that the evaluation is going on crowdsourcing and you have some people and they buy some viewers, however, right? I don't want to be questioned in this regard, right? It's
that's a good point.
I want to have people who are.
That's another dimension.
There's a very political dimension to the whole thing, right? And it's I totally believe what you say, right? And I would use it. I would prefer it whenever possible, but this context is.
It's another dimension.
There's sensitivity somewhere.
Right?
Okay, thanks again. Let's take a break and see. See that. 5 after 4.
So let's leaving right now, or
Then we might be able to maybe finish early, and for those who want to go back to the hotel before the social event can do it. So maybe. So we have 2 presentations now after the break, and then we are done for the day. And, so I think the presentation now is the Shenzhong 2.
He's online.
Yeah. Hello, I'm here. Yeah.
Hello. So please.
So yeah, I'm gonna share my screen. Is my screen visible to the audience?
Yes, you can see it.
Okay. Yeah, cool. So let me slideshow.
Okay, cool. So, yeah, I'm pretty excited to be talking about our latest work on video quality assessment. So, my name is Zemzong Tu, and this is a collaboration between my colleagues at Fudan University and myself. And currently, I am an assistant professor of computer science at Texas A&M University. I graduated from UT Austin, advised by Professor Al Bowick, and my PhD thesis is about video quality assessment and enhancement. So the title of our work is called COVER, Comprehensive Video Quality Evaluator, and this is a work published on CVPR Workshop 2024, and also it is the winning solution of the AI for Streaming 2024 UGC Video Quality Challenge. So a little bit about the background. So UGC video quality is a very challenging and pressing problem because typically we know that UGC videos are pervasive. It's like everywhere on YouTube, Facebook, and some other platforms, UGC platforms. And they are pretty challenging because UGC videos are often suffer from various unpredictable distortions at different levels, from low-level technical such as noise, blur, mid to high-level like aesthetics, because the captured videos often don't have a very good aesthetic quality as well, and also it may have a high-level semantic quality loss because the content may be meaningless or something like you don't feel comfortable about. So this will all affect the user's quality experience when you view these videos at your bedroom, when you view YouTube, view Netflix, but YouTube is more like have a larger diversity of the video quality. And most of the existing video quality models are mainly designed to quantify from the technical aspect, because we all see a lot of the video quality evaluators. They have very good. They are very successful in predicting noise, blur, compression artifacts, but the very last of them has accounted for like a high-level semantic information. So another very good big challenge is that we are now asking for higher resolution and also higher frame rate video. So you want to develop a model that can scale well on high resolution, such as 4K, 60 FPS. And this is like if you see most of the existing state-of-the-art video quality models, they are not able to scale well because they process every pixels and every frame. So if you have a very large video with a very high frame rate, they create a big challenge because like the video quality model will run very slowly. So such that you cannot really meet a lot of the streaming requirements because you need the real-time video quality estimator. So the challenge here brings this very good need that we need to develop a highly efficient and also a very highly performant and comprehensive video quality evaluator for these UGC videos. So here we introduce our model. It's called COVER. So in a snapshot, our model has 3 different branches. We consider both semantic quality, aesthetic quality, and technical quality. So we use 3 parallel branches to get the 3 scores, and then we do a aggregation of the 3 scores and in a final predicted quality score. So you can see here is the demo. So our model can run. This is the input video. This is a snapshot only. And our model can get 3 different aspects of scores, and then also give an overall quality score for the final prediction if you want the overall score. So here we have open source our model. It's all fully publicly available, including the source code, training code, and also the weights. And we also have released a Hugging Face space for you to play with in a web UI. You can just drag your video and get the score in our web demo. I will also do a live demo in the end of our presentation. So let's dive deeper into the details. So we have 3 parallel branches, and for each of the branch, we have a bunch of designs from the beginning to the end. We have temporal sampling, we have spatial sampling, feature extraction, feature fusion, and quality regression to map from the features to the quality scores. Let's dive deeper into each component. So for the temporal sampling, because we want to have a very efficient model, so we only sample very sparse frames because it's based on our previous investigation that video quality is pretty redundant across a temporal axis. So you don't need to really process every frame. So our design is that for the semantic branch, we only sample one frame every second. So no matter how what FPS your video is, we only sample one frame. So this is a key to scale across different FPS, because if you have a 60 FPS, we'll still sample one frame. If you have a 120 FPS, we still sample one frame because we prove that it also works. For the aesthetics, we sample 2 frames every second uniformly. And for the technical, we also sample 2 frames per second. So this is fully from our empirical observation. But I think you can still make it even more efficient if you sample only 1 frame, but at the loss of the performance. So another key aspect is that you don't want to process a high resolution video in the native resolution. So our design is that the semantic branch, we resize the original frame from original to 512 by 512 because it is we use a clip encoder and to get the semantic information. So the clip encoder is pre-trained on this resolution. So we adopt this resolution in the semantic branch. And for aesthetic branch, we resize from the 224 to 224, which is the typical size for image classification model pre-training, because we want to be consistent. Because if there is a domain shift to the pre-trained model, the performance may drop. And for a technical branch, we don't want to do any resizing because resizing will blur the video frame, which is not good for predicting noise or compression artifacts. So we adopt a method proposed by FastVQA, which is called sample fragments, which is we randomly sample patches and then regroup the patches into a video frame. So this doesn't look like a normal video frame, but it's like a regrouping fragments from each patches, sample randomly from the spatial resolution. And then we use a swing transformer to get the feature, which is also pre-trained on some video quality tasks. So we inspired by this paper. So these different branches, we adopt different spatial treatments. So for these 3 branches, for the semantic branch, again, I just mentioned briefly, we use the clip encoder, which is a pretty powerful encoder. So because it is pretty big, it has over 200 million parameters. So we didn't fine tune the whole encoder. We just freeze it and get the feature vectors from the last layer. And for the other 2, we fine tune it because it's pretty small model. The COMNET has about like 20 to 30 million parameters, and the swing transformer is a tiny model. So we fine tune these 2 to get a better alignment to predict the overall quality score. So so this is our kind of empirical adoption. So because these 3 parallel branches doesn't have interactions between each other, so we design another model to interact the features between this, because we assume that the semantic features may have some guidance to these other 2, because the semantic feature is a high level video kind of content understanding, so it may affect the understanding of the other 2 lower level branches. So we propose a channel-wise cross-gating, which is a pretty simple gating mechanism to let the semantic feature to modulate the other 2 features. And then after the modulation, we use a MRP header to map each branch into the final quality score, or to the quality score of the each aspect. Note that our supervision is that we supervise each branch separately, and the loss is that we want each branch to be able to predict the final MOS score. So why we design like this? Because it offers explainability. Because each branch can give a quality score. We'll try the best to get a quality score. So you can use each branch separately, and finally we do a weighted sum of all the scores to get the final score. So our model can use separately for each branch or use together. So you can get 4 scores. You can attribute to what the contribution of each branch has. So these are the benefit of some degrees of explainability, which is better than previous models. So here are our experiments. So we participated in the challenge of the AI streaming video quality challenge, which used the YouTube UGC dataset. And you can see this is a leaderboard from their report. Our model has achieved the best PLCC among the best. It's pretty close to the best, but our model is pretty fast. It can run you can see that our model has only 60 trainable parameters, and the runtime is about 80 milliseconds. And this is tested on 30 frames of 4K resolution. So it is actually pretty challenging. You can see that our model is actually 10 times faster than all the other participants with similar performances. And we are still also a lot faster, 5 times faster than the baselines provided by the officials from their host of this challenge. So here is the evaluation study. We just examine all of our design components. You can see that the first highlighted box shows that each branch can actually get a very high result. So you can see that the technical branch, no doubt, has the best performance because it's attributed more to the overall quality is still mostly determined by the technical quality, such as noise, blur. But you can see that the aesthetics also has a high correlation with the MAU score. And also the semantic branch, to our surprise, also can achieve a high score. So these 3 branch has different correlations, but they account for different aspects, especially for UGC videos. And we also found that combining either the aesthetics branch or the semantic branch with a technical can lead to a significant performance improvement. So it still indicates that we need to consider complemented information when predicting overall quality score. So finally, we add in this simplified channel gating block can further push forward the performance because we want to achieve a high score in the leaderboard. So we design this feature interaction to further improve the feature representation learning capability of our model. So you can see that our final model can achieve a very high quality score, which is a winning solution for this challenge. Also have a great efficiency processing all the videos. So you can see that we shared all the code and base spaces. So now I think I'm gonna show a live demo, which is typically pretty challenging. So I hope that I didn't mess it up. So this is if you scan the QR code of the Hugging Face demo, it's prompt to this website. So here is a very simple UI. So if you click submit, submit nothing. So let me drop the video. Yeah, it's an error because I submit nothing. So let me submit. Okay, let me first in the meantime we will wait. Let me play the video. Yeah, it's like a pretty fun video that you will just watch every day. Like I will watch this funny dogs video on YouTube. So, but you can see that of course the video quality is not pretty good. It's a very small resolution for compression artifacts. So you can see that the generative report from our model has 3 different scores, and you have an overall score. So it's all pretty low because it's a scale from 0 to 5, from worst to best. So you can see that our report is like a very low on all the aspects. So let me try another video, maybe have a high quality. Let me see, submit. You'll see that processing time is almost the same, but this video has a larger resolution, of course. Yeah, it's like a pretty high resolution and pretty clear. It's from YouTube UGC dataset. And you can see that, yeah, it's pretty high. It's of course like overall score is 4.0, and you can see that it's better than 77% of the videos in YouTube UGC. And there's a different quality score from each aspect. And our model says that the aesthetic quality score is the best. That's can be attributed to account for the overall score. So I think with this, I think I have finished my presentation. And if you have any questions, please feel free to bring up now. Thank you very much for your attention.
Joe, any questions?
Question. So, thank you for the presentation and for showing nice demo. I wonder if you found a video that has, technically is perfect, but has very poor aesthetics, whether your predictor would actually correctly, label it that it has very, very high technical content but poor aesthetics. Did you try to kind of, because obviously you have most only in terms of overall quality, but if you pick up a video that is technically perfect but is just looks horrendous in terms of aesthetics, would your metric actually predict that?
Sorry, could you summarize your question, please? So if the video has a I didn't quite get could you summarize it again?
A bit closer. So let's say that if you have a video that technically is perfect, but has poor aesthetics because of poor lighting or anything, would your metric predict that?
So the lighting, I don't think we only predict 3 aspects, right? So I don't know whether lighting can be classified into maybe aesthetics branch. I assume if so, our model can get maybe the statistics is pretty good. It can get a high score in the aesthetics branch, but I don't know because we still train the model end to end. So it may get something about statistics in the aesthetics branch if it's about lighting, and for technical branch, I think it's mainly account for noise, blur, compression. So the overall quality score still is a summation. So we do a average summation. So we don't adjust the weight because we found that simply average summation is the best to secure a high score. So maybe it can capture some sort of, because we didn't specify what attribute. We didn't design the model in an explicit way. We train the model in an implicit way because we just use some priors, because in the aesthetics we use contrastive learning to train the model and then use overall quality score. So it's all in a black box way. It's like implicitly trained. So I don't know, it may not correlate with what you said, like a lighting condition, maybe composition, but it can more or less capture some sort of aspect in an implicit way. So for example, in the technical branch, we do a fragment sampling and then use swing transformer to learn that. Because the technical branch, we do fragment sampling and then the video is not like a normal video. So we should use some local attention to get that, because if you see the patches are pretty random and it's not correlated with the adjacent patches. So it's like a very abnormal video. It's like a composition of the fragments sampled everywhere. So we use this prior to constrain the video to learn, because you have broken semantic information. So we assume that this branch will only learn about the technical aspect. So this is like, we designed the model to learn according to our prior knowledge about the understanding of the distortions, but we don't actually know what specific distortion they learn. For example, like lighting, maybe I guess that the aesthetic branch can capture some sort of lighting condition or statistical video in this Q aesthetic score, but we don't actually know what it learns. So it's more or less trained end to end, and we assume that it can learn some explainability. Yeah, hope this answers your question.
Thank you.
Yeah.
Okay, we have a question online, Pierre.
Yes, thank you for the presentation. So I think this work is like, it make me think a lot about like the model also like Dover, which also like had this idea of aesthetic and technical branch. So actually, most of the question I had actually just got answered. I mean, when you answered the previous question, but I was still wondering about like the data augmentation procedure that you use. I mean, you mentioned that you use contrastive learning. So in this case, you also add like a specific type of impairment. Could you expand a bit on that? I mean, what kind of during the contrastive learning procedure, I mean, what kind of impairment did you consider?
Yeah, thanks. We are actually heavily inspired by Dover. So this idea is actually proposed by Dover. So Dover uses two branches. So you see that the athletics branch, they supervise using two different losses. One loss is that you directly supervise the whole branch using the MOS score. And second loss is the contrastive loss, because we assume that athletics branch is mainly about composition, lighting conditions, or something like the capturing of the video frame. So if you downsample the frame from 1080p to 224, the two different compositions should be the same. So they supervise the using contrastive loss to pull these two frame together, because you assume that these two augmentations, like downsampling is another type, is a type of augmentation. So these two video frame has the same athletics score. So you use contrastive loss to pull these two frames together. And similarly, if you use fragment sampling in technical branch, these two frames should also have the same technical score, because it's originally the patches are the same as sample from this, and we have the prior knowledge that maybe technical branch, technical distortion are many locally. So if you do this fragment sampling, you still have the same technical quality score. So you pull these two frames together as well. So these are all inspired from Dover. So if you check Dover, we have the same pre-training methodology. And our model is actually warm started from Dover. The difference here is that we add a semantic branch using this contrastive learn, this clip encoder, and we use an image encoder from clip to get a semantic branch. And then we also have the fusion block to fuse these three different parallel branches to get a better feature representation learning. So our work is actually built on top of Dover, and also fast. I think Dover is also built on top of fast VQA. So I'm pretty sure you are very familiar with these two works. So we share similar spirits, but our model has a better quality score, and we offer a more comprehensive explainability on top of Dover. Yeah, thanks.
Thank you. I was also wondering, did you apply it also like to different video quality dataset? I mean, because it was like validated on the YouTube UGC, but did you have the chance also like to run it on other existing UGC dataset?
Yes, actually we sorry, I didn't say. Yeah. We do run on 3 different UGC datasets, and we are also expanding our text experiment. So we run on UGC, YouTube UGC, live UGC, and also live VQC and Convid. So we have run experiment on all the existing UGC datasets, and our model is still the best among all the compared ones. Yeah, you can check out our workshop paper. It's
okay.
CVPR workshop.
Yeah. I mean, the results are in your paper. Okay, I see.
Yeah. We provide a more comprehensive result in our papers. So if you scan the code, we have connect every materials there. Yeah, feel free to check out the whole paper.
Okay, great. Thank you very much.
Yeah, thanks.
I also have a question. To my understanding, you have 3 qualities, and then you sum up to get your final score, right?
Yes.
Can you please let us know about the importance of these 3 different qualities on your final score?
Yeah. That's a good question. So we actually we have tried different approaches. So one approach is more like a more reasonable one, as we can think of, is to learn a weighted sum, right? We just learn 3 weights to aggregate the final score. But we think that when you learn that, the weights are more or less similar. So at the end, we just do a simple summation, average summation, and it turned out that it's pretty good already. So we don't use a more complicated one, as we prefer simpler solutions, because in all the model design, we use existing models. We don't use a new model because we rely on some pre-trained models, which is turned out to be already very good. So here we just do simple summation. So maybe you can definitely do a visualization to see for one specific video which quality score is better. But overall, we just try average summation, and it's already good enough. So I believe that these 3 different branches have a similar contribution to the overall score. But if you can also do different experiments to verify which component is more important. But from this, you can see that maybe technical is slightly more important. It's another way of doing that. Is you run each branch and see how it correlates with the human score. So you can see here, the technical is better than aesthetics, better than semantics, which is more or less aligned with our assumption about video quality assessment task. So, but overall, we just do simple average aggregation, which turned out to be already pretty good. So I think they are more or less similar, but from this evaluation study, I think I tend to believe that technical is slightly more important than semantics.
Thank you.
Yeah, thanks.
Okay. Let's thank the speaker again.
Yeah, thanks for the question. Yeah. I'm gonna stop sharing.
Presentation is in ETG, so that would be yeah, that's Enrique. Aurelio.
Hi, did you say my name, Shell?
Yeah.
Okay, sure. Well, I thought my presentation was at 6.
Ahead of schedule, so
Yeah, sure. I can present if it's possible. Yeah, sure.
Yeah, please go ahead.
Okay, good. Okay. Yeah, let me just share the screen. Forgot to do that. Yes. Allow me just a second here. Let me turn the camera on. Okay, great. I hope you guys can see me. Good afternoon, everyone. And my name is Enrique Rossi. I'm a PhD student working in Luleå University of Technology in north of Sweden. Karameter, which is not here in the meeting, he is my main advisor. Krister Uland and Irina Kotanis are also my co-advisors. And now I would like to present my most recent work, with the title Subjective Quality of Experience Assessment for Virtual Reality Cloud-Based First-Person Shooter Game. This work has been presented in the conference ICC from IEEE 2024 last month. Well, the cloud game market is expanding, and very recently it has migrated to the metaverse by first being accessible in VR devices. This makes gaming accessible anywhere at any time, so long as a good and reliable internet connection exists between the users and the data centers. Cloud game is a streaming service which requires optimal network conditions. As you know, game events happen in real time, and they expect from the users fast and response input reaction to the game events as they occur. Unfortunately, mobile networks are not that reliable. They are often affected by a variety of issues, which causes network conditions such as high delay, jitter, and packet loss. On top of that, VR experiences are very sensitive to problems due to the proximity and also the immersiveness between the users and the devices. If we don't carefully look into the effect of these network conditions on the user's gaming experience, this emerging service will never see the light in real life. That's why we say the stakeholders, which are the game developers, network operators, and cloud service providers, they should take into account these network conditions. These network conditions, these network conditions are provided over mobile networks for VR cloud gaming services. However, some of these stakeholders, they don't have access to performance metrics from the video streaming. They might only rely on the network layer information, which are quality of service factors, such as jitter, delay, and packet loss. Hence, it becomes imperative for us to study the sole effect of these metrics and their effect on the user's quality of experience for VR cloud gaming services. The current research in quality of experience for VR cloud game has so far focused on limited ranges of one-way delay, RTT, and packet loss. And these ranges, they do not cover mobile network conditions, which are often affected by jitter and the combinations of RTT and packet loss. Hence, considering these limitations and knowing how important it is to study this quality of service for understanding VR cloud game users' quality of experience, we propose to answer the following research question. How do mobile broadband network conditions affect VR cloud gaming services and the user's perceived quality of experience? To answer this question, we took the necessary steps to conduct a user evaluation. We invited 30 users, and then we invite them to play this game called Serious Sam VR, The Last Hope. This is a shooter game. Enemies comes in different waves, and the users are required to shoot the enemies in order to survive. We invited them to play this game in a lab environment built to emulate network conditions. The game was running in a computer and streamed to a thin client, which was a MetaQuest 2 VR device, using the streaming technology, NVIDIA CloudXR. Between the streaming, we had a computer which was emulating network conditions through NetM. However, we used also a tool that we had developed called Altruist, which called the NetM API to pass the network conditions the correct time, and also to collect many different data important to this experiment. In total, we emulated 28 network conditions, 8 conditions for RTT, 3 conditions for packet loss, 8 conditions for the combinations of RTT and packet loss applied together, and then 9 conditions for jitter. We used a normal distribution to generate the jitter values, and we varied the distribution mean between 25 to 75 milliseconds, and the distribution width between 1 and 6 standard deviations. We applied these network conditions in both links, up and down link. Then after we applied one of the conditions for one game match, we asked the user to play at the end of the match to answer, the following question. How do you rate the overall quality of your gaming experience in a scale of 1 to 5, 1 being very poor, 5 being very good? With that, every user actually tested all the conditions. We gave the conditions in a randomized balanced Latin square order. And then with that, we were able to compute the mean opinion score for each network condition. And now I will show the results. The purple box means we didn't see a clear effect or minor effect from the conditions in the mean opinion score for quality of experience, while the orange score means there is a clear effect. And now for the RTT conditions, this one box in the left, we see that the quality of experience was degraded the most by values larger than 75 milliseconds. This is for RTT. For packet loss, we perceived a significant effect on the mean opinion score for quality of experience for values larger than 6%. For the combined conditions of RTT and packet loss, we only perceive a degradation in the group of 75 milliseconds RTT for the conditions, for all the conditions, packet loss conditions we tested, 0, 2, and 4%. Now, for the jitter conditions, we perceive that the most important thing was not the jitter mean, meaning 25, 50, or 75 milliseconds. However, the most important one was actually the width of the distribution, and the value of 3 standard deviations and larger was the most important, or the one that degraded the most, the mean opinion score for VR Cloud Game. In addition, we have done a study to understand how the logs from the CloudXR for certain metrics, such as throughput and frames per second, they were affected by the emulated network conditions that we have applied. And now, regarding throughput, this is what these results are for. We see that the most significant, let's say, effect we were able to perceive was for packet loss conditions, and also for random jitter. As you see, as an example, for random jitter with standard deviations larger than 3 or 6, we saw that CloudXR reduced the throughput to almost 5 megabits per second from the original value, which was 65 megabits per second. When it comes to frames per second, we have seen the biggest, or the most negative effect was perceived for the RTT conditions. As an example, if you look at the RTT of 175 milliseconds in this orange box, you'll see that the drop in frames per second was almost 44% from the original value, which was target at 72 Hertz. As a final step from our research, we decided to investigate whether in practice, in real mobile networks, whether a VR Cloud game could be hosted and what quality or it would be, happen. To do that, we actually pinged 5 different AWS, Amazon Web Services data centers spread throughout Europe from our city in the north of Sweden. We pinged these data centers for 7 days using the same network operator, but then 4 different network connections: 4G, 5G non-standalone, 5G standalone, and then wire. And in the meantime that we pinged them, we collected the round trip time and the jitter. And then, based on the results we have collected, we can say that for wired connections, VR Cloud Game could be hosted within Europe with a very small impact on the actual quality for the users. However, for mobile 4G and 5G non-standalone, we perceive an average to heavy impact in the quality for VR Cloud Game due to the large amount of jitter that we have encountered. For 5G standalone, the latest 5G technology, we perceive an average impact on the mean opinion score, because although the jitter was smaller than the other 2 mobile technologies, it's still large enough to cause an effect on the quality. In summary, to the best of our knowledge, we are the first to investigate the combined effect of RTT and packet loss and varying configurations or parameters for jitter on quality of experience for VR Cloud Game users. We are also the first to conduct subjective chess using a commercial VR Cloud Game solution, NVIDIA CloudXR, and to investigate how their performance metrics reported by this service were affected by emulated network conditions. And also to do an assessment whether the current broadband mobile networks, 4G, 5G, and 5G standalone, could possibly host VR Cloud Game existing data centers. In the future, we plan to propose models that can predict the quality of experience based on these VR Cloud Game services. Also to investigate a different game through subjective chess and build a new data set and partake into IoT standardization activities. Thank you so much for your attention. This is a QR code for the preprint of the paper, in case you are interested to check all the results. And if there is time for questions, Joe, I'm not sure if there is, I'll be happy to answer them. Thank you.
You have questions?
I can have questions. So the two ways to stream content to VR headset, either you simulate a big screen in VR or you stream actual 360 3D content. Which one was used in your experiment?
Thank you for the question. Should just allow me. Yeah, this is an image of the experiment setup that we had. And the way we did is the game was being generated in a screen in a computer. The screen was full HD, and then CloudXR captures the whole screen, and then it sends through the network to another application that runs in the VR device, where it receives the stream and then show it to the user.
So essentially, your VR headset was a big screen, so you didn't have 3D.
Yes.
Okay. Thank you.
Yeah, and then if the user moves the headset, then CloudXR thin client captures the input from the user, the head movement, and then sends back to the computer.
Yeah, but did you use ASW, asynchronous space warp, to compensate for head movement and any latency?
Oh no, we just use the technology as it was, like as it is provided to the public. We actually I'm not so sure if this is something they have implemented. I would need to check the streaming technology in this case. We have only installed the application in the PC and also in the VR device, and then we apply the network conditions like in the middle of it based on the connections we had in the lab.
Thank you.
Thank you so much.
Any other question? You mentioned this altruist, that is the tool to set up the experiment, right?
Yes.
And that's open source?
Yes, well, this tool we have developed actually to help us in a previous experiment that we have conducted for mobile cloud game. And then we have ever since improved the tool. And yes, it is open source. We have also write up a paper about this tool for QMX actually last year. We are still improving the tool, and but anyway, the community is more than welcome to use it. We are also trying to use this tool in upcoming activities with the barbecue project for cloud game. They are also intended to use that tool as well. It helps quite a lot because here we have many devices. As you see, 2 computers, there is a tablet where we actually show the questionnaire to the users. The users were asked to take the headset off and then answer the quality of experience question. And all of these were automatically done, showing the question, interrupt the game, start the game again, collect the PCAP files, and collect the CloudXR logs from inside of the device. All of this was done in real time by the tool, because otherwise it would have been very hard for us to manage all these things and still, keep up with the time, so we don't waste users' time and we don't cause like more biases because of these user evaluations.
And if you go to the QR code you had at the end, will you find the software there?
Well, no, this actually the QR code for the paper, but if you I cannot see because it's very small here in my screen, the person that is asking the question, but I can send it to you, the information, or I can put it in the chat if it's possible, the link for the tool, in case you're interested to check it out.
And then I can put it in the link into the minutes.
Okay, it would be very helpful. Thank you so much.
Okay, any other? Okay, let's thank Enrique again.
Thank you.
Yeah, I think that concludes the sessions for today. The only remaining item is to approve the minutes. So let's do that, and we can close for today. Share my screen. Okay, we had a little bit of trailing information from yesterday. That was the Cracovia session that was run by Nikolai and presented by Nikolai, and also now the information is in the minutes. Started today with ADHD, having presentation by Anja, Thomas, Dominic, and Syed. And then we went into IMG. Okay, that is big. Someone could just copy that into the minutes, that would be great. And we had the admin section that wasn't really, more giving 2 action points for me to set up an audio call about it for the board, and then Nikolai to draft the proposal for the new working group.
Apologies, just a correction. HFVE from HEFE.
Sorry?
It's
HFE. Ah, okay, sorry, yeah, okay, good. Okay. Yeah, on the phone. Okay, great. Norm. We got a presentation on Philippines and MPEG, Norm, cover model, and then Enrique's presentation. And there is the link to this software. Yeah, that could be useful for doing experiment for cloud gaming. And then nothing else. Can we approve the minutes so far? Okay, great, thank you. Let's close the session for today. We get some extra time to maybe go back to the hotel for